Imagine a night sky with no stars, no planets, and no light. Just an endless, cold, and empty darkness. The universe, once full of energy and life, is now at its final stage. But how will it all end? Will everything collapse in a fiery disaster, break apart, or simply fade away? Scientists have wondered about this for centuries, studying different ideas, from a massive Big Crunch to a slow and quiet heat death. So, what will really happen when the universe reaches its final moments? Let's take a look into the far future and explore the eerie possibilities that lie ahead. In the early 20th century, scientists believed that the universe was static and unchanging. They thought that the stars and galaxies were fixed in place and that the universe had always existed in its current form. However, this belief was about to be challenged in a dramatic way by an American astronomer named Edwin Hubble. His groundbreaking discovery in the late 1920s revealed that the universe was not static, but actually expanding. A revelation that changed our understanding of the cosmos forever. Before Edwin Hubble's research, the common scientific view was that the Milky Way galaxy was the entire universe. Many astronomers believed that all the stars, nebulae, and celestial objects were confined within the Milky Way, and they debated whether mysterious cloud-like objects called nebulae were simply parts of our galaxy or separate star systems. At the time, a Dutch astronomer named Willem de Sitter had already proposed a model in which the universe could be expanding. But there was no solid observational proof to confirm this idea. Additionally, Albert Einstein, whose general theory of relativity had been published in 1915, initially believed in a stable universe. In fact, when his equations suggested that the universe should be expanding or contracting, he introduced a cosmological constant to force a static solution. Later, he would regret this modification, calling it the biggest mistake of his career. Edwin Hubble was working at the Mount Wilson Observatory in California, using the most powerful telescope of that time, the 100-inch Hooker telescope. In the 1920s, he studied distant nebulae to determine their nature. Were they simply clusters of gas and dust within the Milky Way, or were they separate galaxies beyond our own? By meticulously observing a particular type of star called Cepheid variables, Hubble was able to determine distances to these nebulae. Cepheid variable stars have a unique characteristic. Their brightness changes over time in a way that directly relates to their true luminosity. By measuring how bright they appeared from Earth and comparing this to their actual luminosity, Hubble could calculate their distance. To his astonishment, Hubble found that some of these nebulae were far beyond the boundaries of the Milky Way. This meant they were not just parts of our galaxy, but entirely separate galaxies, each containing billions of stars. This discovery alone was revolutionary because it showed that the universe was far larger than anyone had previously imagined. However, Hubble's most important breakthrough came when he examined the light from these distant galaxies. He noticed that their light was stretched towards the red end of the spectrum, a phenomenon known as redshift. The redshift effect occurs when light waves are stretched as an object moves away from the observer. This effect is similar to the change in pitch of a siren as an ambulance moves away from you. The sound waves stretch, causing a lower pitch. In the case of galaxies, their light waves were stretching, indicating they were moving away from Earth. Hubble compared the redshift of different galaxies and discovered a pattern. The farther away a galaxy was, the faster it was moving away. This relationship, now known as Hubble's law, was the first clear evidence that the universe was expanding. It was a monumental discovery that overturned the long-standing belief in a static universe and laid the foundation for modern cosmology. Hubble's work had profound implications for our understanding of the cosmos. If the universe was expanding, then it must have been smaller in the past. This idea eventually led to the Big Bang theory, which suggests that the universe began from an incredibly dense and hot state and has been expanding ever since. The discovery also reshaped the way scientists thought about time and space. Instead of being a fixed, eternal structure, the universe was dynamic, constantly changing and evolving. This realization opened the door to new questions. What is the ultimate fate of the universe? Will it continue expanding forever, or will it eventually collapse back on itself? What caused the expansion in the first place? Einstein, who had previously resisted the idea of an expanding universe, visited Hubble in 1931 and personally examined the evidence. Realizing that his original equations had correctly predicted an expanding universe, he abandoned his cosmological constant and embraced the idea of cosmic expansion. Hubble's law states that the speed at which a galaxy is moving away is directly proportional to its distance from us. Determining the exact value of the Hubble constant has been a major challenge for astronomers. Over the years, different methods have provided slightly different values, leading to debates about the precise rate of expansion. Nevertheless, Hubble's fundamental discovery remains uncontested. The universe is expanding, and this expansion can be measured. One of the biggest consequences of Hubble's discovery was the eventual development of the Big Bang theory. If galaxies are moving away from each other now, it means that in the distant past, they must have been much closer together. If we rewind time far enough, all matter in the universe must have once been concentrated in an extremely dense and hot state. This idea was first proposed by a Belgian priest and astronomer, Georges Lemaitre, in 1927. Lemaitre suggested that the universe started from a primeval atom, or a cosmic egg, that exploded, giving rise to all matter and space. At first, many scientists were skeptical, but as more evidence, including Hubble's work, emerged, the Big Bang theory gained acceptance. Today, nearly a century after Hubble's discovery, the Big Bang theory remains the leading explanation for the origin of the universe. Modern telescopes and space observatories, such as the Hubble Space Telescope, named in his honor, continue to gather evidence supporting this theory. Edwin Hubble's discovery revolutionized our understanding of the cosmos. His work not only confirmed that the universe was far larger than previously thought, but also revealed its dynamic nature. Thanks to Hubble, we now know that the universe is constantly expanding, a concept that has shaped modern astronomy and physics. The Hubble Space Telescope, launched in 1990, has provided some of the most detailed images of distant galaxies, deepening our understanding of the universe's structure and evolution. It has allowed scientists to measure the expansion of the universe with greater precision, and has even contributed to the discovery of dark energy, a mysterious force accelerating the expansion. Hubble's contributions to astronomy extend far beyond his own time. His observations set the foundation for cosmology, inspiring generations of scientists to explore the mysteries of the universe. The questions raised by his discovery about the beginning, structure, and fate of the universe continue to drive scientific research today. Edwin Hubble's discovery of cosmic expansion was one of the most important breakthroughs in the history of science. Before his work, the universe was thought to be static and limited to the Milky Way galaxy. His observations proved that the universe is much larger and is continuously expanding, leading to the development of the Big Bang theory and modern cosmology. How do scientists measure how fast galaxies are moving away from each other? The answer lies in something called the Hubble constant. This is a number that represents the rate of expansion of the universe. Hubble's original calculations in the 1920s estimated the expansion rate, but as technology improved, scientists refined this number. Today, there is still some debate about the exact value of the Hubble constant. Different methods produce slightly different results, but the general estimate is around 70 kilometers per second per megaparsec. To understand what this means, let's break it down. A megaparsec is a unit of distance used by astronomers, equal to about 3,260,000 light-years. 70 kilometers per second per megaparsec means that for every 3,260,000 light-years of distance, a galaxy moves away at an additional 70 kilometers per second. This might not seem like a lot at first, But when you consider the vast size of the universe, the numbers quickly add up. The farther away a galaxy is, the faster it appears to be moving. This confirms that the universe is expanding at an increasing rate. If galaxies are moving away from each other, what will happen in the distant future? Scientists have proposed several possible scenarios based on the behavior of the universe's expansion. One of the most widely accepted theories is that the universe will continue expanding forever. If dark energy keeps pushing galaxies apart, space will become so vast that galaxies will no longer be able to interact. Over billions and trillions of years, stars will burn out, galaxies will drift away, and the universe will become a cold, dark place. This scenario is known as the Big Freeze. Another possibility is that the expansion of the universe will not only continue, but will accelerate to an extreme level. In this scenario, dark energy would become so powerful that it would eventually tear galaxies, stars, and even atoms apart. This catastrophic end to the universe is called the Big Rip. If this happens, everything we know will be destroyed in the far future. A third theory suggests that the expansion might one day slow down and reverse. Instead of galaxies moving apart forever, gravity could pull everything back together, causing the universe to collapse in on itself. This event is known as the Big Crunch. Some scientists believe that this could lead to another Big Bang, restarting the universe in a never-ending cycle. Understanding how galaxies move away from each other is not just about looking at the stars. It helps us answer fundamental questions about the nature of the universe, time, and existence itself. The discovery that galaxies are moving apart provides strong evidence for the Big Bang theory, which suggests that the universe began from an extremely hot and dense point about 13,800 million years ago. This changed our entire view of cosmic history. Since dark energy is the force driving the universe's accelerated expansion, studying it could reveal new physics beyond what we currently know. Some scientists even believe that understanding dark energy could help us develop new technologies or uncover hidden aspects of reality. By measuring how fast galaxies are moving apart, we can make educated guesses about what will happen in the future. Whether the universe ends in a big freeze, a big rip, or something else entirely, these discoveries help us prepare for the long-term fate of the cosmos. The universe is not just expanding, it is expanding at an increasingly faster rate. This discovery was one of the most surprising in modern physics. For a long time, scientists assumed that gravity would eventually slow down the expansion of the universe. However, in the late 20th century, astronomers studying distant supernovae found something unexpected. Instead of slowing down, the universe's expansion was speeding up. This strange and mysterious force pushing the universe apart is called dark energy. Dark energy makes up about 70% of the entire universe, yet we barely understand what it is. Unlike ordinary matter and even dark matter, dark energy does not seem to interact with anything in a way that can be directly measured. Its only known effect is its ability to stretch space itself, driving galaxies apart at an ever-increasing speed. But what exactly is dark energy? Where does it come from? And how does it continue to shape the fate of the universe? For most of human history, people thought the universe was unchanging. However, in 1929, the famous astronomer Edwin Hubble made a groundbreaking discovery. By observing galaxies, he found that they were all moving away from us. Not only that, but the farther away a galaxy was, the faster it was receding. This was the first strong evidence that the universe was expanding. For many years, scientists debated what would happen in the long run. Gravity, the force that pulls objects together, was expected to slow the expansion. Some thought that if the universe did not have enough matter, it would expand forever, but at a slower and slower rate. Others believed that if there was enough matter, gravity would eventually stop the expansion and cause the universe to collapse in a big crunch. However, in 1998, two teams of astronomers studying distant exploding stars known as Type Ia supernovae found shocking evidence. These supernovae serve as standard candles, meaning they shine with a predictable brightness. By measuring how dim they appeared, scientists could estimate their distance. The data showed that these supernovae were farther away than expected, meaning that the universe's expansion was not slowing down, it was accelerating. Dark energy is one of the biggest mysteries in modern science. Although it makes up the majority of the universe, we cannot see it, touch it, or measure it directly. There are several leading ideas about what dark energy might be. One of the simplest explanations is something called the cosmological constant. This idea was first introduced by Albert Einstein in his equations of general relativity in the early 20th century. At that time, Einstein believed the universe was static, not expanding or contracting. To make his equations fit this belief, he added a term called the cosmological constant, which acted as a repulsive force balancing gravity. However, when Edwin Hubble discovered the expansion of the universe, Einstein abandoned the idea, calling it his biggest mistake. But after the discovery of dark energy, scientists revived the cosmological constant as a possible explanation. The cosmological constant suggests that empty space itself has an energy, sometimes called vacuum energy. As the universe expands, new space is created, and with it, more of this energy, which continues to push galaxies apart. This idea matches current observations well, but it raises another question. Why does this energy have the specific strength that it does? Another possibility is that dark energy is not constant, but changes over time. Some scientists propose that dark energy comes from a force field called quintessence, which evolves as the universe expands. Unlike the cosmological constant, which is the same everywhere and at all times, quintessence could have different strengths in different parts of the universe. If quintessence is real, it might explain why dark energy only began dominating the universe's expansion in the last few billion years. However, there is no direct evidence for quintessence yet, and scientists are still searching for ways to test this idea. Some researchers believe that dark energy is not a separate force at all, but rather a sign that our understanding of gravity is incomplete. According to this idea, gravity might behave differently on very large scales than it does within galaxies and solar systems. Some alternative theories, such as fifth force theories or extra dimensions, attempt to explain dark energy as a result of a modified version of general relativity. However, testing these ideas is extremely difficult because gravity has been well tested on smaller scales, and no obvious violations of Einstein's theory have been found. Dark energy is not just a small detail, it is shaping the destiny of the entire universe. Depending on how dark energy behaves in the future, scientists predict several possible outcomes. If dark energy remains constant or grows stronger over time, the universe will continue expanding forever. Galaxies will move farther apart until they can no longer see each other. Stars will eventually run out of fuel and burn out, leaving a cold, dark universe filled with scattered black holes and dead stars. If dark energy increases in strength over time, it could eventually become so powerful that it tears everything apart. First, galaxies would be pulled away from each other. Then, dark energy would overcome the forces holding stars, planets, and even atoms together. In the final moments, even subatomic particles would be ripped apart. Some theories suggest that dark energy might reverse itself in the distant future, causing the universe to stop expanding and then contract. This would lead to a big crunch, where all matter collapses back into a single point, possibly triggering another Big Bang. This could mean that the universe goes through endless cycles of expansion and contraction. Since dark energy cannot be directly seen, scientists rely on indirect methods to study it. Some of the most important ways they investigate dark energy include supernova observations. By studying distant supernova, astronomers can measure how the expansion of the universe changes over time. Cosmic microwave background, CMB. The faint radiation left over from the Big Bang carries clues about the early universe and how dark energy influenced its evolution. Baryon acoustic oscillations, BAO. These are patterns in the distribution of galaxies that help scientists understand how dark energy has shaped cosmic structures. Large-scale galaxy surveys. Telescopes like the Dark Energy Survey and the Euclid Space Telescope map millions of galaxies to track the effects of dark energy. Whatever dark energy turns out to be, it will redefine our understanding of the universe. As scientists build better telescopes and collect more data, we may one day uncover the true nature of this mysterious force. Until then, dark energy remains a cosmic puzzle, one that holds the key to the ultimate fate of the universe. For a long time, scientists have wondered about the fate of the universe. Will it keep expanding endlessly? Will it slow down and eventually stop? Or could it even reverse and collapse in on itself? To answer this, we have to look at the forces shaping the universe and the discoveries made by astronomers over the past century. Right now, most scientists believe that the universe's expansion will continue forever. The discovery of dark energy in the year 1998 showed that instead of slowing down, expansion is accelerating. If this continues, the universe will likely head toward the Big Freeze or Big Rip scenario. However, dark energy remains one of the biggest mysteries in science. We still do not fully understand what it is or whether it might change over time. Some scientists speculate that unknown forces or new physics could alter the fate of the universe. For example, if dark energy weakens or behaves differently over time, expansion might slow down, possibly leading to a future big crunch. If new discoveries reveal hidden forces at work, they could completely change our understanding of cosmic evolution. Some theories suggest parallel universes or higher dimensions could play a role in how our universe evolves. Stars, the massive glowing balls of gas that light up the universe, are not eternal. They are born, they shine for millions or even billions of years, and then they die. This grand cycle of stellar life is fueled by nuclear reactions in their cores, where hydrogen atoms fuse to form helium, releasing an enormous amount of energy in the process. However, this fuel is not infinite. At some point, every star, no matter its size, will run out of energy. When that happens, the star's fate depends on how massive it is. Some stars will fade quietly, while others will go out in spectacular, violent explosions. Before we discuss how stars die, it's essential to understand how they live. Stars are born from vast clouds of gas and dust scattered throughout space. These clouds, known as nebulae, contain mostly hydrogen, the simplest and most abundant element in the universe. Under the pull of gravity, parts of these clouds begin to clump together, growing denser and hotter. Eventually, the temperature in the core becomes so intense, reaching millions of degrees, that nuclear fusion begins. This marks the birth of a star. The star's entire life depends on this process of nuclear fusion. It acts like a cosmic engine, providing the immense heat and light we see from Earth. For the majority of a star's existence, it stays in a stable phase known as the main sequence, where the outward pressure from nuclear fusion balances the inward pull of gravity. However, this balance does not last forever. As the star consumes its hydrogen fuel, its core begins to change, leading to dramatic transformations that will eventually result in its death. But not all stars meet the same fate. Their final destiny depends on their size. Stars that are much smaller than our Sun, called red dwarfs, burn their hydrogen very slowly. These stars can last for an astonishingly long time, trillions of years. In fact, because the universe itself is only around 14 billion years old, no red dwarf has reached the end of its life yet. Scientists predict that when they do, they will simply cool down and fade away into small, dark remnants called black dwarfs. The Sun, a medium-sized star, will have a different fate. It has already burned for nearly 5 billion years and has about the same amount of time left before it exhausts its fuel. When it begins to run out of hydrogen, it will swell into a red giant, expanding so much that it could engulf planets like Mercury, Venus, and even Earth. During this phase, the Sun will begin burning helium, producing heavier elements like carbon and oxygen. However, this process is unstable. In the end, the Sun will shed its outer layers, creating a beautiful glowing shell of gas called a planetary nebula. The remaining core, now exposed, will shrink into a white dwarf, a small, incredibly dense object about the size of Earth, but with nearly the same mass as the Sun. Over billions of years, this white dwarf will cool and dim until it too fades into darkness. For stars much larger than the Sun, their deaths are far more dramatic. These stars burn through their fuel much faster, sometimes lasting only a few million years. Once they exhaust their hydrogen, they start fusing heavier elements in a layered structure, like an onion. Each new element burns at a different temperature, producing new energy sources. However, this process has a limit. When the core of a massive star starts fusing iron, it signals the beginning of the end. Unlike lighter elements, iron does not release energy when fused. Instead, it absorbs energy, making the core unstable. Gravity takes over in an instant, causing the core to collapse at an incredible speed. This sudden collapse triggers a supernova, one of the most powerful explosions in the universe. Supernovae are so bright that they can outshine entire galaxies for weeks. They scatter heavy elements like gold, silver, and uranium into space, seeding the universe with the building blocks for new stars, planets, and even life itself. What remains after the explosion depends on the mass of the original star. If the star was moderately massive, the leftover core would become a neutron star, an object so dense that a teaspoon of its material would weigh as much as a mountain. Neutron stars sometimes spin rapidly, emitting beams of radiation that sweep through space like cosmic lighthouses. These are called pulsars. However, if the original star was truly enormous, its core would collapse even further, forming a black hole, a region of space where gravity is so strong that nothing, not even light, can escape. Black holes are among the most mysterious objects in the universe, capable of warping time and space itself. As time moves forward, all stars will eventually run out of fuel. The biggest ones will explode, the smaller ones will quietly fade, and over trillions of years, even the remnants like white dwarfs and neutron stars will cool down and disappear into the darkness. Scientists predict that in the far, far future, possibly a number followed by 100 zeros of years from now, the universe will enter a state known as the heat death. By then, all stars will have died, and the universe will be a cold, dark, and empty place, with black holes slowly evaporating and the last traces of light fading into the void. The universe is filled with countless stars, each one a massive ball of burning gas that lights up the night sky. But just like everything else in nature, stars have a life cycle. They are born, grow, change, and eventually die, transforming into different celestial objects. The journey of a star can take billions of years, and the final stage depends on the star's size and mass. Some stars become red giants before shrinking into white dwarfs, while others collapse into neutron stars or even black holes. Let's take an in-depth journey through the fascinating life cycle of a star, breaking it down step by step in simple and exciting terms. The nebula stage. Every star starts its life inside a nebula, a massive cloud of gas and dust floating in space. These nebulae are often called stellar nurseries because they are the birthplaces of new stars. The gas in a nebula is mostly hydrogen, the most abundant element in the universe. Over millions of years, gravity slowly pulls the gas and dust together. As the cloud gets denser, the temperature begins to rise. Eventually, a dense clump called a protostar forms. At this stage, the young star is still gathering mass and has not yet started shining. After several million years, the protostar gets hot and dense enough for a powerful process to begin: nuclear fusion. This is when hydrogen atoms smash into each other and merge to form helium, releasing an enormous amount of energy. This energy is what makes a star shine. Once fusion begins, a new star is born. The main sequence stage, the longest phase of a star's life. Once a star starts shining, it enters the most stable and longest-lasting phase of its life, the main sequence. This stage can last for billions of years, depending on the star's size. Small stars, like our Sun, can stay in this phase for about 10 billion years. Massive stars, which are much larger than the Sun, burn through their fuel much faster and may only last a few million years. During this period, the star continuously converts hydrogen into helium through nuclear fusion. This process releases a huge amount of heat and light, which counteracts the force of gravity trying to pull the star inward. This balance keeps the star stable. For example, our Sun has been in the main sequence phase for around 4.5 billion years and is expected to continue shining for another 5 billion years before moving to the next stage. The red giant stage. The star expands and cools. When a star runs out of hydrogen fuel in its core, it faces a big problem. Without the pressure from nuclear fusion pushing outward, gravity starts squeezing the star inward. However, fusion doesn't stop completely. Instead, it moves to the outer layers of the star, causing it to expand and cool down. At this point, the star becomes a red giant. Small and medium-sized stars, like the Sun, grow into red giants that can expand up to 200 times their original size. Larger stars grow into red supergiants, which are even bigger and more dramatic. Because red giants are much larger, their outer layers become cooler, which is why they appear reddish in color instead of bright white or yellow. As a red giant, the star begins to fuse heavier elements like helium, carbon, and oxygen. But this stage doesn't last forever. Eventually, the star runs out of fuel completely, leading to its next transformation. For stars that are about the size of our Sun, the next step is becoming a white dwarf. Once a red giant has burned up all its fuel, it cannot continue nuclear fusion. The outer layers of the star are blown away, forming a beautiful cloud of gas known as a planetary nebula. What remains is the hot, dense core of the star, now a white dwarf. A white dwarf is incredibly small and dense. Even though it is only about the size of Earth, it has nearly the same mass as the original star. This means that a single teaspoon of white dwarf material would weigh millions of tons. White dwarfs do not create new energy. They simply glow from leftover heat and slowly cool down over billions of years. Eventually, they fade into darkness, becoming black dwarfs, cold, dead remnants of stars. However, since the universe is only around 14 billion years old, scientists believe that no black dwarfs exist yet because white dwarfs take trillions of years to cool completely. For stars much larger than the Sun, the story does not end with a white dwarf. Instead, they explode in a supernova, one of the most powerful events in the universe. A supernova occurs when a massive star runs out of fuel and its core collapses under its own gravity. This collapse happens so quickly that it creates an enormous explosion, blasting outer layers of the star into space. This explosion is so bright that for a short time it can outshine an entire galaxy. After a supernova, what remains is an incredibly dense object known as a neutron star. Neutron stars are some of the strangest objects in space. They are only about 10 to 20 kilometers wide, but contain more mass than the Sun. This means they are so dense that a single sugar cube-sized piece of neutron star material would weigh as much as 1 billion tons. Neutron stars spin extremely fast, sometimes hundreds of times per second, and some of them emit beams of radiation. These rapidly spinning neutron stars are called pulsars, and they send out pulses of light that can be detected from Earth. If a dying star is even more massive, at least 20 times the size of the Sun, it doesn't just form a neutron star. Instead, the collapse is so intense that it forms a black hole. A black hole is a region in space where gravity is so strong that nothing can escape, not even light. This makes black holes completely invisible. Scientists can only detect them by observing how they affect nearby stars and gas clouds. At the center of a black hole is a point called the singularity, where all the mass is crushed into an infinitely small space. Surrounding the singularity is the event horizon, the point beyond which nothing can return. Black holes come in different sizes. Stellar black holes form from collapsing stars. Supermassive black holes exist at the centers of galaxies, including our Milky Way. These are millions or even billions of times the mass of the Sun. Right now, the universe is still forming new stars, but this process will not continue forever. Stars need fuel, hydrogen and helium to form. Over time, as stars burn through these elements, there will be less and less material available to create new ones. Scientists predict that in about 100 trillion years, written out as 100 million years, the last stars will form. After this, the universe will enter a period called the degenerate era, when no new stars can be born. Once all the existing stars have burned out, the universe will become a dark, cold place. There will be no more sunlight, no warmth, and no glowing galaxies. The universe will be filled with dead stars, black holes, and cold remnants like white dwarfs and neutron stars. During this era, the only light in the universe will come from white dwarfs slowly cooling down, but they will eventually turn into cold, dark objects called black dwarfs. Occasional collisions of dead stars, which might release brief bursts of light. Hawking radiation from black holes, a slow process in which black holes lose tiny amounts of energy over time. For a very, very long time, far longer than the current age of the universe, these remnants will float through space, slowly losing their heat. But even this will not last forever. Black holes are some of the last remaining objects in this dark universe. They are formed from the collapse of massive stars and can remain for an incredibly long time. However, according to physicist Stephen Hawking, black holes are not truly eternal. Hawking discovered that black holes emit a faint form of radiation, now called Hawking radiation. Over trillions and trillions of years, this radiation will slowly cause black holes to lose energy and shrink. Eventually, after a mind-bogglingly long time, far longer than the lifetime of any star, all black holes will completely evaporate. When the last black hole disappears, the universe will be left with nothing but empty space. With no stars, no galaxies, and no black holes, what happens next? The final stage of the universe is often referred to as the heat death or the big freeze. This is when the universe reaches a state of maximum entropy. In simple terms, entropy is the measure of disorder. Over time, energy spreads out and everything becomes more uniform. Once all energy is evenly distributed, there is no longer any movement, no heat, and no possibility for anything new to happen. In this final stage, the universe will be completely cold, dark, and lifeless. There will be no planets, no stars, and no galaxies, just a vast emptiness that stretches endlessly in all directions. If this scenario sounds bleak, that's because it is. However, some scientists believe there could be other possibilities for the distant future of the universe. The Big Bounce. Instead of ending in heat death, the universe could eventually collapse in on itself and restart in a new Big Bang. Quantum fluctuations. Some theories suggest that, given infinite time, tiny fluctuations in empty space could eventually give rise to a new universe. The multiverse theory. Our universe may not be the only one. If parallel universes exist, there could be other places where stars still shine and life continues. However, nothing lasts forever. One day the last star will burn out, The black holes will fade, and the universe will settle into a cold, dark silence. Whether this is truly the end, or just the beginning of... The heat death of the universe, also called the Big Chill or Big Freeze, is a theory about how the universe might eventually come to an end. According to this idea, one day, the universe will reach a point where all the energy is evenly spread out. At that point, no useful energy will be available to keep things moving or changing. This means that all processes, like stars burning, planets orbiting, and even atomic reactions, will stop because there will be no way to transfer energy from one place to another. Now, this does not mean the universe will reach a specific freezing temperature. Instead, it means that everything will be at the same temperature, no matter how low it gets. In scientific terms, this is called thermodynamic equilibrium, a state where no energy flow is possible and nothing new can happen. If the universe is shaped in a way that is either flat or hyperbolic, a specific type of curved shape, or if a mysterious force known as dark energy keeps pushing space outward forever, then the universe will never stop expanding. If this happens, scientists believe that heat death is inevitable. Over an unimaginably long time, the universe will keep cooling down until it reaches a very low and stable temperature where nothing can function anymore. The concept of heat death comes from the second law of thermodynamics, which states that entropy, a measure of disorder, always increases over time in an isolated system. In simple terms, this means that things naturally move toward chaos and energy spreads out. If we apply this rule to the entire universe, it suggests that over time, energy will become so evenly distributed that no useful work can be done. The idea was first introduced in the 1850s by a scientist named Lord Kelvin. He realized that if energy keeps spreading out and nothing replenishes it, then eventually all movement in the universe will stop. He even used this theory to argue that the universe could not have existed forever, because if it had, it would have already reached this lifeless, energy-balanced state. Long before Kelvin's work, a French astronomer named Jean-Sylvain Bailly suggested something similar in the year 1777. He believed that all planets have an internal heat that slowly fades away over time. According to his view, planets go through different stages of heating and cooling. He thought Venus was still too hot for life and would need thousands of years to cool down, while Mars had already become too cold to support life. Eventually, he predicted, everything in the universe would reach an equilibrium where all movement would stop. If this theory is correct, the universe is headed toward a cold, dark, and lifeless future. All stars will burn out, black holes will eventually disappear, and even atomic particles may break apart over an incredibly long period. When that happens, the universe will be nothing but a vast, empty space with a constant temperature, an ultimate stillness where time, as we know it, would no longer matter. The concept of the heat death of the universe comes from the fundamental principles of thermodynamics, which describe how energy behaves. The idea was first loosely suggested in the middle of the 19th century by Lord Kelvin, whose real name was William Thomson. He built upon earlier ideas about energy loss from scientists like Sadi Carnot, James Joule, and Rudolf Clausius. Over the next 10 years, his theories were expanded by Hermann von Helmholtz and William Rankine. The heat death idea is based on the first two laws of thermodynamics and how they apply to everything in the universe. In the year 1851, Lord Kelvin stated that heat is not a physical substance, but a form of energy. He explained that heat and mechanical work are connected, like cause and effect. A year later, in 1852, he published a paper called On a Universal Tendency in Nature to the Dissipation of Mechanical Energy. In this work, he explained what we now know as the second law of thermodynamics. He pointed out that energy used for motion eventually spreads out and becomes less useful. This idea gained attention from other scientists, including William Rankine and Hermann von Helmholtz, and they shared ideas on the topic. In the year 1862, Kelvin wrote another paper called On the Age of the Sun's Heat, where he discussed how energy cannot be destroyed, the first law of thermodynamics, but it does become less useful over time as it spreads out, the second law. He suggested that over time, heat would become evenly distributed across the universe, leading to a state where no useful work could be done. This meant that eventually all motion and energy use would stop. One way to imagine Kelvin's idea is to think of a clock. If a clock runs down, it eventually stops working unless someone winds it up again. Kelvin wondered if the universe was like a giant clock that would eventually stop. He speculated that reversing this process, restoring lost energy and making the universe young again, would require an extraordinary force, something like an act of creation. This became known as Kelvin's paradox, which questioned the idea that the universe could be infinitely old. If the universe had existed forever, then it should have already reached a state of complete energy spread, meaning no stars or heat differences should exist. However, since stars still shine and heat differences still exist, this suggests the universe has not been around forever. After Kelvin's publications, both Helmholtz and Rankine credited him with the idea of heat death and the paradox that challenged the belief in an eternal universe. Helmholtz described heat death as the final state of the universe, while Rankine called it the end of all physical phenomena. Over time, scientists proposed different ideas about the universe's future. In the late 20th and early 21st centuries, new theories emerged. Some suggested that if the universe keeps expanding forever, it could eventually face heat death, or a more violent end known as the Big Rip, where everything is torn apart. If the universe has a positive cosmological constant, a value related to its expansion, then rather than reaching absolute zero, it would settle at a very low but non-zero temperature, with no more useful energy left to do work. The heat death theory suggests that from the moment of the Big Bang until now, the universe has been full of galaxies, stars, and cosmic structures that keep energy moving. Since energy is still in motion today, the universe is not yet in its final state. However, in the extremely distant future, everything could change. For example, massive black holes, which are expected to grow even larger, will eventually evaporate. A black hole with the mass of an entire galaxy, about 100 billion times the mass of the Sun, is expected to take about 1 followed by 100 zeros years to completely disappear due to Hawking radiation. Some black holes might grow even bigger, taking an unimaginable one followed by 106 zeros years to fade away. After that, the universe will enter a stage known as the dark era, where almost nothing happens. It will mostly contain a very thin, cold gas of tiny particles like photons and leptons. At this point, energy levels will be extremely low, and time will stretch out over mind-bogglingly long periods. Some scientists speculate that a second inflationary period might happen, meaning the universe could expand again in a new way. Others suggest that if our universe is in a temporary energy state, it could collapse into a different, lower energy state. If none of these events occur, then heat death will be the final state, an endless, motionless universe where nothing happens. There is, however, one last possibility. Over unbelievably long timescales, the universe might experience a tiny, random decrease in entropy, disorder, due to rare statistical events known as thermal fluctuations. According to a theory called the Poincaré recurrence theorem, if you wait long enough, possibly around 1, followed by a number with 56 zeros years, random quantum effects might create a new universe. This would be an extraordinary event, essentially starting everything all over again. The fate of the universe remains uncertain, but if the heat-death theory is correct, then far into the future, all movement and energy will be gone, and the universe will become a dark, empty void. However, with possibilities like quantum fluctuations, some scientists believe that even this state might not be truly final. Entropy is one of the most mysterious and debated concepts in physics, especially when applied to the universe as a whole. The famous physicist Max Planck once said that the phrase entropy of the universe does not really make sense because there is no precise way to define it. In the year 2008, physicist Walter Grandi pointed out that humanity still knows very little about the universe, so trying to define its entropy is premature. He also questioned how anyone could measure thermodynamic entropy in a universe that has never been in a state of perfect balance. Similarly, Laszlo Tisza argued that if a system is not in equilibrium, it is impossible to assign an entropy value to it. Hans Adolf Buchdahl took an even stronger stance, saying it is completely unjustified to assume that the universe can be treated as a closed thermodynamic system like a sealed container of gas in a laboratory experiment. Physicist Giovanni Gallavotti also highlighted a major challenge. There is no single agreed-upon definition of entropy for systems that are not in equilibrium, even if they appear to be in a steady state. The problem becomes even bigger when discussing entropy in chaotic and constantly changing conditions. Elliot H. Lieb and Jacob Ingvason noted that although most physicists believe in the idea of non-equilibrium entropy, no one has been able to define it in a way that is universally accepted and fully satisfying. Peter Landsberg shared a similar view, warning that applying thermodynamics, and especially entropy, to the entire universe without deeper investigation is misleading. He suggested that while the question is intriguing, any answers we currently have are mostly speculative. An analysis from the year 2010 reinforced these doubts. It stated that the entropy of a general gravitational field remains unknown and that gravitational entropy is extremely difficult to measure. However, this analysis did propose one major insight. The universe likely has far more entropy than previously estimated. The reason for this? Supermassive black holes. According to the study, these colossal cosmic objects contribute more to the universe's total entropy than anything else. Physicist Lee Smolin expanded on this idea by discussing gravity's role in shaping the universe's energy balance. He explained that gravity prevents the universe from reaching thermal equilibrium. Unlike typical systems where energy loss slows things down, gravitational systems behave in a strange way. Their parts move faster as they lose energy. This means they don't settle into a uniform, balanced state, but instead become more complex and fragmented over time. This perspective is further supported by a more recent experiment, which found that even in a simple, closed system, a stable, non-equilibrium steady state can exist. This suggests that when an isolated system breaks into smaller subsystems, it does not necessarily reach thermodynamic equilibrium. Instead, entropy can shift from one part of the system to another without being produced, which does not violate the second law of thermodynamics. The concept of entropy in the universe remains an open question. While many scientists suspect that non-equilibrium entropy exists, they have not yet found a way to define or measure it properly. Meanwhile, new discoveries, especially those related to black holes and gravity, continue to challenge traditional thermodynamic assumptions, making this one of the most fascinating mysteries in modern physics. The ultimate fate of the universe is a big mystery in the field of cosmology, the study of the universe's origin, structure, and future. Scientists have developed several theories about how the universe might evolve over time and what its final destiny could be. These ideas are based on actual observations and scientific principles rather than myths or religious beliefs. Some theories suggest that the universe has existed for a limited period, while others propose that it might have always existed. Understanding how the universe began and where it is headed remains one of the biggest questions in science. In the early 20th century, an astronomer named Edwin Hubble made a groundbreaking discovery. Between the 1930s and 1950s, he observed that galaxies were moving away from each other. This led to the idea that the universe started from a very dense and hot state around 13,787 million years ago. This concept became known as the Big Bang theory. Scientists have since confirmed the theory by measuring the universe's expansion rate, the amount of matter it contains, and the properties of energy in space. Today, most scientists agree that the universe is flat, meaning that if you draw two perfectly straight lines, they will never meet or bend apart. They also believe the universe will keep expanding forever. However, to fully understand the universe's origin and fate, scientists must study several factors, including the movement of galaxies, the universe's overall shape, and the mysterious substances known as dark matter and dark energy. The idea of predicting the universe's future became possible in 1915, when Albert Einstein introduced his famous theory of general relativity. His equations describe how gravity shapes the universe on a large scale. Over the years, scientists have found multiple solutions to these equations, each suggesting a different possible ending for the universe. In 1922, a mathematician named Alexander Friedmann proposed different solutions to Einstein's equations, and in 1927, a Belgian scientist named Georges Lemaitre expanded on these ideas. One of their solutions suggested that the universe had been expanding from an extremely small and dense point, a moment now known as the Big Bang. Then, in 1929, Edwin Hubble observed a specific type of star, called a Cepheid variable, in distant galaxies. His measurements confirmed that the universe was indeed expanding. This discovery changed the way scientists thought about the cosmos. In 1927, Georges Lemaitre officially introduced what would later be known as the Big Bang theory. However, in 1948, another scientist, Fred Hoyle, introduced a competing idea called the steady-state theory. This theory suggested that while the universe was expanding, it always remained roughly the same because new matter was constantly being created. These two theories were debated for many years until an important discovery in 1965 changed everything. That year, two scientists named Arno Allen Penzias and Robert Woodrow Wilson found evidence of cosmic microwave background radiation, leftover energy from the early universe. This discovery strongly supported the Big Bang theory and led most scientists to accept it as the best explanation for how the universe began. Interestingly, Albert Einstein himself originally believed that the universe was static, meaning it neither expanded nor shrank. When he realized that his own equations suggested the universe could be expanding, he introduced something called the cosmological constant to make the math fit a static universe. However, when Edwin Hubble proved that the universe was indeed expanding, Einstein admitted that adding the cosmological constant was the biggest mistake of his life. One important concept in studying the fate of the universe is something called the density parameter, often represented by the Greek letter omega. This number helps determine whether the universe will expand forever, eventually stop expanding, or even collapse back in on itself. Depending on whether omega is equal to, greater than, or less than 1, scientists classify the universe as flat, closed, or open, respectively. If the universe contains mostly ordinary matter, its fate is closely tied to its shape. That is why scientists have spent years measuring omega to predict what will ultimately happen to the universe. In 1998, astronomers made a shocking discovery. By observing supernovas or exploding stars in distant galaxies, they found that the universe's expansion was not slowing down as expected. It was actually speeding up. This led to the idea that an unknown force, now called dark energy, was pushing the universe apart. Scientists still do not fully understand what dark energy is, but one possibility is that it is a form of energy that exists everywhere in space, constantly driving the universe to expand faster. Researchers are still trying to figure out whether dark energy stays the same over time or changes as the universe grows. Some think it could be linked to a strange quantum field that existed in the early universe. To solve this mystery, scientists are relying on advanced space telescopes such as Euclid, the Nancy Grace Roman Space Telescope, and the James Webb Space Telescope, along with powerful new ground-based observatories. These tools will help refine our understanding of dark energy and possibly reveal new insights into the ultimate fate of the universe. The future of our universe depends on three main factors: its overall shape, the amount of dark energy it contains, and a key formula called the equation of state, which determines how dark energy changes as the universe expands. Scientists studying the universe have gathered strong evidence that, starting around 7.5 billion years after the Big Bang, the universe's expansion has been speeding up. This supports the idea of an open universe, meaning that the universe might keep expanding forever. However, data collected by the Wilkinson Microwave Anisotropy Probe suggests that the universe is either completely flat or extremely close to being flat. If the total density of the universe, represented by the Greek letter omega, is greater than 1, then space is curved like the surface of a giant sphere. In such a universe, the sum of the angles inside a triangle would add up to more than 180 degrees, and straight lines would eventually meet instead of remaining parallel. This type of universe follows an elliptic geometry. In a closed universe, gravity would eventually slow down the expansion of space until it completely stops. After that, the universe would begin to shrink, pulling everything inward until all matter collapses into a single point. This event is called the Big Crunch, which is like a reversal of the Big Bang. However, if dark energy is strong enough, it could counteract gravity and cause the universe to keep expanding indefinitely, even in a closed universe. The most widely accepted model today, known as the Lambda Cold Dark Matter Model, Lambda CDM, suggests that dark energy makes up about 68% of all the energy in the universe. According to this model, for gravity to overpower dark energy and make the universe collapse, the amount of matter in the universe would have to be about 17 times more than what scientists currently measure. If omega is less than 1, then space is curved in a completely different way. It would have a shape similar to a saddle. In this kind of universe, the angles inside a triangle would always add up to less than 180 degrees, and lines that start out close together would continuously grow farther apart. This type of geometry is called hyperbolic. In an open universe, gravity is not strong enough to stop the expansion. Instead, the universe would continue growing larger forever, with galaxies and other celestial objects moving farther and farther apart. If dark energy remains a dominant force, the expansion will not only continue, but accelerate, possibly leading to a scenario where galaxies become so distant from each other that in the far future they will no longer be visible from one another. These possibilities give us different ways to imagine the fate of the universe, whether it will collapse into a final singularity, stretch endlessly into the void, or find some other unexpected fate. Scientists have found that even if dark energy didn't exist, a universe that is negatively curved, meaning its shape is somewhat like a saddle, would still keep expanding forever. Gravity would slow this expansion a little, but never enough to stop it. However, when dark energy is present, something remarkable happens. Instead of just continuing at a steady pace, the expansion speeds up over time. If dark energy continues pushing the universe outward, it could lead to one of two extreme outcomes. One possibility is what scientists call heat death, or the Big Freeze, a state where the universe becomes so vast and stretched out that all heat and energy are evenly spread, making life and activity impossible. The other, even more dramatic possibility is called the Big Rip. In this scenario, dark energy becomes so powerful that it overcomes not just gravity, but also the fundamental forces holding atoms and molecules together. Over time, galaxies, stars, planets, and even the smallest particles would be torn apart, leaving nothing but scattered radiation drifting endlessly. But what if the universe had a negative cosmological constant? This means it would have a kind of negative energy that counteracts expansion. Instead of stretching forever, even an open universe, one that isn't tightly curved, would eventually stop expanding and collapse inward in what is known as the Big Crunch, a fate where everything falls back together, possibly leading to another cycle of birth and rebirth. The geometry of the universe depends on something called critical density, a balance between gravity and expansion. If the universe's average density exactly matches this critical value, then the universe is considered flat. In a flat universe, the angles of a triangle always add up to 180 degrees, just like in ordinary geometry, and parallel lines never meet or diverge. Measurements from the Wilkinson microwave anisotropy probe show that the universe is extremely close to being flat, with only a tiny margin of error of less than 0.5%. If there were no dark energy, a flat universe would keep expanding forever, but at a continually decreasing speed, never quite stopping, but also never accelerating. However, because dark energy exists, the expansion initially slows due to gravity, but eventually speeds up. This means the ultimate fate of the universe would be similar to an open universe, one that never stops expanding. Scientists believe the fate of the universe depends largely on its density. So far, most evidence suggests that the universe will keep expanding indefinitely. If this is true, it will eventually lead to what is called the Big Freeze, a scenario where temperatures drop lower and lower until the universe becomes a lifeless void. In this future, stars will continue forming for between 1 trillion to 100 trillion years. However, as time goes on, the gas needed for new stars will run out. Without fresh fuel, existing stars will gradually burn out, one by one, leaving behind a universe that grows colder and darker. Over incredibly long periods, black holes will take over as the dominant cosmic structures, but even they won't last forever. Due to Hawking radiation, black holes will slowly evaporate, vanishing into nothingness over an unimaginable span of time. Some theories suggest that over an infinite period, rare fluctuations could cause temporary reversals of entropy, leading to brief, random bursts of order in the otherwise chaotic void. However, this idea remains theoretical. The Hubble constant is what scientists use to measure the expansion rate of the universe. Right now, its value is high enough to increase the distances between galaxies, but not strong enough to tear them apart. If, however, this expansion rate were to keep increasing indefinitely, it could eventually destroy all matter in the universe. At some point, even atoms and fundamental particles would be ripped apart, leaving nothing but isolated energy in a state that resembles a singularity, an ultimate, final breakdown of the universe itself. One especially extreme possibility involves phantom dark energy, a mysterious form of energy with properties that could make expansion happen even faster than other models predict. If this turns out to be true, the Big Rip could occur much sooner than expected, leading to a sudden and violent end of everything. The Big Crunch hypothesis presents a fascinating idea about how the universe might eventually meet its end. It suggests that just as the universe began with a massive explosion known as the Big Bang, it could one day stop expanding and start shrinking instead. If the universe contains enough matter and energy, the force of gravity could eventually overcome its outward expansion, pulling everything inward. This would cause galaxies, stars, planets, and even space itself to collapse into an incredibly small and dense point, possibly a singularity, similar to how the universe was before the Big Bang. However, scientists are not entirely sure if this will happen. Some studies indicate that the universe is expanding at an accelerating rate, which makes the Big Crunch seem unlikely. But because our observations have only covered a tiny fraction of the universe's lifetime, there is still a small chance that things could change in the distant future. One particularly intriguing possibility is that the universe could go through endless cycles of expansion and collapse. According to this idea, after the universe is crushed into a tiny, super-dense state during the Big Crunch, a new Big Bang could occur, giving birth to another universe. This could have happened countless times before and may continue forever. This concept is called the cyclic universe or oscillating universe theory. But there's a major issue with this idea. It contradicts the second law of thermodynamics, which states that disorder or entropy always increases over time. If the universe kept collapsing and restarting, entropy would continue building up with each cycle, eventually leading to a state where no useful energy remains. This would result in a heat death, where nothing could happen anymore. Because of this, many scientists have moved away from the cyclic universe model. A variation of the cyclic model is called the Big Bounce theory. Instead of the universe being destroyed by an ultimate collapse, this theory suggests that a strange force, possibly related to quantum mechanics, could prevent a total singularity from forming. Instead of a complete end, the universe would bounce back from the collapse, creating a new cycle of expansion. This means that our universe may have been born from the remains of a previous one, and if true, it could mean that the universe has no true beginning or end, just endless cycles of rebirth. Some versions of the Big Bang theory also propose that the universe may not have started as a singularity at all. Instead, quantum mechanics suggests that the universe tunneled into existence, meaning it emerged from something unknown rather than from an infinitely small and dense point. This aligns better with what we know about quantum physics, which challenges the idea of absolute singularities. While current evidence suggests that the universe is expanding too fast to ever collapse, we still don't have all the answers. Future discoveries in physics and cosmology might change our understanding of the universe's fate. Whether it ends in a big crunch, keeps expanding forever, or follows a pattern of big bounces, the ultimate destiny of the universe remains one of the greatest mysteries of science. Scientists have proposed several possibilities for how dark energy might behave, but all of them are based on simple assumptions. The truth is, we still know very little about dark energy or how it really works. If the theory of cosmic inflation is correct, then in the earliest moments after the Big Bang, the universe was dominated by a different kind of dark energy. This period eventually came to an end, which suggests that the properties of dark energy were much more complex than what scientists assume today. There is also a chance that dark energy could change again in the future, leading to an event with unpredictable consequences. Since both dark energy and dark matter remain mysterious, some even consider them hypothetical, it is impossible to know exactly what role they will play in the universe's future. One possible catastrophic event linked to dark energy is known as the Big Slurp. This theory suggests that the universe is currently in a false vacuum, a temporary, unstable state. If this false vacuum suddenly shifted into a more stable, true vacuum state, it could trigger a massive, universe-altering event. To understand this theory, it's important to know about the Higgs field, which fills the universe much like an invisible force field. This field has different energy levels, similar to how an electromagnetic field works. If the universe is already in its lowest possible energy state, then nothing drastic will happen. But if it's in a higher energy, false vacuum state, there is a chance that it could suddenly tunnel into a lower energy state, a process known as vacuum decay. If vacuum decay were to occur, it could completely change the fundamental laws of physics. Even the basic constants that govern the universe, such as the forces holding atoms together, might be altered, leading to a reality where matter, energy, and even the fabric of space and time itself no longer function as they do now. In some scenarios, this transformation could happen instantly, wiping out all structures in the universe without any warning. However, the entire universe would not be destroyed by the Big Slurp. Only a portion of it would be affected. This is because galaxies that are more than 4,200 megaparsecs, about 13 billion light-years, apart, are moving away from each other faster than the speed of light. Since the Big Slurp itself would not be able to expand at light speed, most of the universe would remain untouched. For perspective, the observable universe, the part we can see from Earth, spans about 46 billion light-years in every direction. Scientists believe the actual universe is at least that big, if not much larger. To determine which of these theories is more likely, researchers weigh the universe by measuring how much matter, radiation, dark matter, and dark energy contribute to its overall density. They also compare different theories with real-world data, such as how galaxies are clustered together, how distant supernovae behave, and tiny temperature variations in the cosmic microwave background, the faint glow left over from the Big Bang. The Big Crunch is a fascinating idea about how the universe might end. In this scenario, the universe, after expanding for billions of years, eventually stops growing and begins to shrink. Everything in existence, from galaxies to atoms, would be pulled back together by gravity. Over time, the universe would collapse into an incredibly dense and hot point, similar to how it all began with the Big Bang. Some theories even suggest that after the universe reaches this point, a new Big Bang could occur, creating a cycle of destruction and rebirth. However, most scientific evidence today suggests this idea is unlikely. Observations of distant galaxies show that the universe isn't slowing down. It's actually expanding faster and faster. This points to a different, more chilling scenario called the Big Freeze, in which the universe expands forever, growing colder and darker until all energy is spread too thin to sustain life. The idea of the Big Crunch dates back to the year 1922, when Russian physicist Alexander Friedmann developed equations describing how the universe could evolve. According to his work, whether the universe expands forever or eventually collapses depends on how much matter it contains. If there were enough matter, gravity would eventually halt the expansion and pull everything back together, much like how a thrown ball eventually falls back to the ground due to Earth's gravity. In this scenario, the universe wouldn't just shrink, it would implode in an extreme and violent collapse. As it contracts, all of its energy and radiation would be squeezed into a smaller and smaller space. Stars would heat up dramatically, and their surfaces might ignite as they are crushed together. Near the end, the entire universe would become a raging fireball, reaching unimaginable temperatures. In the very last moments, time and space themselves would cease to exist. Some scientists believe that the Big Crunch might not be the final chapter. They propose an even wilder idea: the Big Bounce. According to this theory, when the universe collapses to an extreme point, it doesn't stay there. Instead, it bounces back and triggers a new Big Bang, starting the entire cosmic cycle all over again. If this theory is correct, the universe could go through endless cycles of expansion and contraction, a process called the cyclic universe. For many years, scientists debated whether the universe would end in a Big Crunch or continue expanding forever. Then, in the late 1990s and early 2000s, astronomers made a groundbreaking discovery. By studying distant exploding stars, supernovas, and mapping the faint radiation left over from the Big Bang, the cosmic microwave background, they realized that the universe isn't just expanding, it's speeding up. This meant that rather than collapsing, the universe is racing toward a cold and empty future. In recognition of this discovery, physicists were awarded the 2011 Nobel Prize in Physics. The idea that the universe might eventually collapse isn't new. In the 17th century, an English scholar named Richard Bentley wrote to the famous physicist Isaac Newton with a puzzling question. He wondered, if the universe is finite and gravity pulls everything together, wouldn't all the stars eventually collapse into a single point? And if the universe is infinite, wouldn't the stars feel equal forces from every direction, preventing any movement at all? This question, known as Bentley's paradox, was one of the earliest versions of the Big Crunch idea. Today, we know that stars move constantly and that the universe is expanding, which explains why they don't collapse into a single point. Albert Einstein originally believed that the universe was unchanging, meaning it neither expanded nor contracted. In the year 1917, he worked with a Dutch astronomer named Willem de Sitter to test whether his famous theory of general relativity could support a universe that remained still. Willem de Sitter's calculations suggested that a simple version of the universe could exist within this framework. At first, everything seemed to make sense, and scientists adopted this idea to describe how the universe worked. However, they soon encountered a variation of an old problem known as Bentley's paradox, which challenged their understanding. Despite supporting a static universe, Einstein's own theory of general relativity actually suggested that the universe was always in motion, either expanding or contracting. This created a contradiction because back then, astronomers believed the universe was unchanging. To make his model work, Einstein introduced an extra force that acted like anti-gravity, pushing against the pull of gravity to keep the universe balanced. This force was named the cosmological constant, a mathematical addition to his equations meant to prevent the universe from collapsing under its own gravity. Then came a groundbreaking discovery. In the 1920s, Edwin Hubble, working at the Mount Wilson Observatory, measured the distances of galaxies and compared them with redshifts, a phenomenon where light from distant objects stretches toward the red end of the spectrum. These red shifts had been studied earlier by two astronomers, Vesto Silfer and Milton Humason. When Hubble combined their findings with his own distance measurements, he noticed something shocking. The farther away a galaxy was, the faster it was moving away from Earth. Hubble carefully mapped out this relationship using data from 46 galaxies and calculated what is now called the Hubble constant. His initial estimate was 500 kilometers per second per megaparsec, which is much higher than today's accepted value. However, the most important takeaway was that the universe was expanding, meaning it was not static at all. When Einstein learned of Hubble's discovery, he quickly abandoned the cosmological constant. His original equations actually predicted an expanding or contracting universe on their own. But since this contradicted what scientists believed at the time, he had introduced the constant to force a static model. Realizing his mistake, Einstein later called it the biggest blunder of his career. In the year 1931, he traveled to meet Hubble personally and thanked him for laying the foundation of modern cosmology. From that point forward, the old idea of a static universe was discarded, and scientists fully embraced the concept of an ever-expanding universe. However, some scientists have proposed an alternative idea called the Big Bounce hypothesis. This theory suggests that the universe might not expand forever. Instead, it could eventually collapse back into a tiny, dense state, similar to how it began, before exploding into a new Big Bang. If this is true, the universe might be stuck in an endless cycle of expansion and contraction, constantly being reborn in an infinite series of Big Bangs and Big Crunches. In the year 1931, the brilliant physicist Albert Einstein briefly considered the idea of a cyclic universe. He proposed that before the Big Bang, there might have been another universe that collapsed in an event known as the Big Crunch. This catastrophic collapse, he suggested, could have triggered a new Big Bang, restarting the cycle all over again. In this view, our universe might not be a one-time occurrence, but part of an endless process of expansion and contraction, repeating itself forever. Since then, scientists have built upon this idea, developing more detailed models of cyclic universes. One of the most well-known modern theories is called the ekpyrotic model, introduced by physicist Paul Steinhardt. This theory suggests that the Big Bang wasn't a unique event, but rather the result of two enormous, parallel cosmic structures, called branes, colliding in a higher dimensional space. According to this model, our entire universe exists on one of these branes, floating within a larger multidimensional reality. When the two branes crash into each other, it leads to a cycle of destruction and rebirth, much like Einstein's Big Crunch and Big Bang concept. What we see today, matter, radiation, and the structure of the universe could be the result of tiny quantum fluctuations that existed before this cosmic collision. Over billions of years, our universe expanded and evolved into what it is now, but the theory suggests that in several more billion years, it will start to contract again, leading to another cycle. A mysterious force known as dark energy, which exists between these branes, could be responsible for resolving certain long-standing scientific problems, such as why the universe appears so flat and why we don't observe magnetic monopoles, which were once predicted by earlier models. This means that the universe may have been cycling through infinite past and future cycles, with each cycle resetting the conditions of reality. One major challenge for previous models of cyclic universes was the buildup of entropy, essentially disorder, which over time would lead to a state of heat death, where the universe becomes lifeless and inactive. The ekpyrotic model proposes a solution by suggesting that with every cycle, the universe undergoes a small net expansion, preventing entropy from accumulating indefinitely. However, this model isn't without its challenges. Scientists still don't fully understand the nature of branes, as they are deeply connected to string theory, a branch of physics that remains highly theoretical. Additionally, some researchers argue that the intense collapse of a big crunch might destroy the delicate balance needed to preserve the structure of the universe in the next cycle. While scientists have a good understanding of cosmic inflation, the rapid expansion of the universe after the Big Bang, and how vacuum fluctuations shape the universe, there is still no confirmed candidate from particle physics that fits perfectly into this model. Another take on the cyclic universe idea comes from physicist Roger Penrose, who introduced a theory known as conformal cyclic cosmology, or CCC. According to this idea, the universe continues expanding until all matter decays into pure energy, transforming everything into light. At this point, the universe no longer has any meaningful concept of size or time, essentially resetting itself and becoming identical to the state it was in before the Big Bang. In other words, the end of one universe smoothly transitions into the birth of the next, continuing this cycle indefinitely. Penrose, along with researcher Vahe Gurzadian, suggested that clues supporting this theory might be found in the cosmic microwave background, CMB, the faint radiation left over from the Big Bang. They believed that certain patterns in this radiation, such as uniform temperature rings, could be the remnants of gravitational waves from previous cycles. However, as of the year 2020, no conclusive evidence for CCC has been found. Despite its intriguing nature, this model also has its critics. Some physicists argue that for the transition between cycles to work, all particles in the universe would have to lose their mass as the universe ages. This remains a major point of contention. Penrose, however, remains confident in his theory, presenting evidence of unusual circular patterns in the CMB that he believes are caused by gravitational waves from black hole collisions in a previous cosmic cycle. According to CCC, our current universe is just one aeon in a never-ending sequence, where each aeon begins with a new Big Bang and eventually fades into another. While these theories are fascinating, they are still highly speculative. Scientists continue searching for more evidence, hoping to unlock the mysteries of our universe's past, present, and future. If any of these models turn out to be correct, it would mean that the universe we see today is just one chapter in an eternal story, one that has been unfolding for longer than we can possibly imagine. Loop quantum cosmology is a theory about the universe that suggests a fascinating idea. Instead of the universe starting with a sudden explosion known as the Big Bang, it could have gone through a cycle of expansion and contraction, forming a quantum bridge between different phases of existence. In this model, space and time behave differently than in traditional physics. When the universe is stretched out and vast, this effect is too small to notice. But when the universe shrinks down to an extremely tiny size, at what scientists call the Planck scale, a new force becomes so strong that it overpowers regular gravity. This force prevents the universe from collapsing into a single point, something that Einstein's general theory of relativity predicts as a singularity. Because this model avoids singularities, it forces scientists to rethink fundamental questions about the universe, such as why different regions of space look so similar. Instead of the Big Bang, this theory introduces the idea of the Big Bounce, a cycle where the universe contracts to a very small but non-zero size and then expands again, endlessly repeating. The concept of effective dynamics has been used in loop quantum cosmology to help scientists describe what happens during these extreme moments. Advanced computer simulations have shown that this method works well, though in cases where the universe had a lot of quantum uncertainty at later stages, the model's predictions can be slightly off. However, even in those cases, the overall behavior of the universe is still accurately captured. Scientists have also explored the idea that the current expansion of the universe, driven by dark energy, could one day reverse, leading to contraction instead of expansion. If a mysterious energy field known as quintessence is responsible for dark energy, and if its strength drops below zero, then the universe could start shrinking as soon as the next 100 million years. Some researchers, including André Ijas and Paul Steinhardt, argue that this fits well with the idea of a cyclic universe, one that goes through endless cycles of expansion and contraction. They predict that this contraction phase could last for about 1 billion years before the universe begins expanding again in a new cycle. Physicist Paul Davies proposed an alternate scenario where, instead of bouncing back into expansion, the universe continues shrinking until it collapses completely in an event called the Big Crunch. In this model, this catastrophic collapse would happen roughly 100 billion years from now. As the universe contracts, galaxies would merge, and the temperature of space would rise as light waves get compressed. Eventually, stars would be packed so close together that they start colliding. About 500,000 years before the final collapse, the radiation in space would become hotter than the coolest stars, causing them to overheat and evaporate. This process would continue with hotter stars until even the largest and most massive stars disappear about 100,000 years before the final moment. In the last minutes before the Big Crunch, the temperature would become so extreme that atoms themselves would break apart. All matter in the universe would then be pulled into gigantic black holes. At the very end, everything would be crushed into an unimaginably tiny, infinitely dense, and scorching hot point, similar to the state of the universe before the Big Bang. Some theories suggest that this could be followed by another Big Bang, leading to the birth of a completely new universe. These ideas challenge our understanding of time and existence itself. Could the universe be eternal, constantly rebirthing itself in a cycle of expansion and contraction? Or will it one day reach a final state, never to change again? While we don't yet have definitive answers, research in quantum physics and cosmology continues to push the boundaries of what we know, bringing us ever closer to unraveling the mysteries of the cosmos. Imagine a future where the universe, as we know it, doesn't just expand forever, but gets stretched so much that everything, galaxies, stars, planets, and even the smallest atoms, gets ripped apart. This terrifying and fascinating concept is known as the Big Rip. It's one of the most extreme predictions about the ultimate fate of the universe, and if it turns out to be true, it means that everything we know, from the tiniest particles to the largest cosmic structures, will one day be destroyed in the most dramatic way possible. But what exactly is the Big Rip? How does it work? And when could it happen? If the Big Rip happens, it won't occur all at once. It will unfold in a series of devastating stages, each more dramatic than the last. Scientists estimate that if this doomsday scenario is real, it could happen in about 20 billion years from now. Here's how it would play out. First, the expansion of the universe will continue as usual. Galaxies will keep moving away from each other, just like they are today. However, as dark energy's power grows stronger, galaxies that were once bound together by gravity will begin to separate. The cosmic web of galaxies that stretches across the universe will start to unravel. A few billion years before the final moments, dark energy will become so powerful that even the force of gravity inside individual galaxies won't be able to hold them together. The Milky Way and all other galaxies will begin to break apart, with their stars flinging away into the vastness of space. As the Big Rip gets closer, dark energy will overpower even the gravitational pull that holds solar systems together. Our Sun and its planets, including Earth, will no longer orbit in a stable way. Planets will drift away from their stars, floating into the darkness, lost forever. With galaxies and solar systems gone, dark energy will continue its destruction. It will grow so powerful that even individual stars will no longer hold themselves together. The Sun and all other stars in the universe will be ripped apart, their atoms scattered across space. But it doesn't stop there. Eventually, even planets, moons, and all solid matter will begin to break apart at the atomic level. The force that holds atoms together, known as the strong nuclear force, will be overwhelmed by dark energy. In the very last moments before the Big Rip, even the fundamental building blocks of reality, protons, neutrons, and electrons, will be torn apart. Nothing will be left except a universe filled with isolated particles drifting endlessly in the void. At this point, the universe will be completely unrecognizable. There will be no galaxies, no stars, no planets, and no life. Just a vast emptiness, stretching forever. The universe itself will have been ripped apart, leaving behind nothing but scattered energy. The idea of the Big Rip is based on our current understanding of dark energy, but there's still a lot we don't know. Scientists are working hard to uncover the true nature of dark energy and determine whether this terrifying future is possible. Some researchers believe that dark energy might change over time. Instead of growing stronger, it could weaken, leading to a different fate for the universe. For example, if dark energy fades away, the universe's expansion could slow down, possibly leading to the Big Crunch, where everything collapses back into a single point. Others think that dark energy might be constant, meaning the universe would continue expanding forever, but at a steady rate, avoiding the Big Rip entirely. This scenario is called the Big Freeze, where galaxies drift apart but remain intact, and the universe slowly becomes cold and dark over trillions of years. If the Big Rip is real, then we are living in an era where the universe is still relatively stable. There's no immediate danger. After all, this event, if it happens, is at least 20 billion years away. That's far longer than the lifespan of the Sun, which will burn out in about 5 billion years. But studying these extreme ideas helps scientists understand the true nature of the universe and its fate. The more we learn about dark energy, the better we can predict what will happen billions of years from now. Phantom energy is not just any ordinary force, it is a form of dark energy that becomes stronger over time. Unlike gravity, which weakens as objects move apart, phantom energy does the opposite. It increases in strength as space expands. This means that the more the universe grows, the harder this mysterious force pulls everything apart. The concept of phantom energy comes from equations that describe the energy density of space. Scientists use a mathematical value called the equation of state to measure how different forms of energy behave. When this value is lower than -1, the energy is classified as phantom energy. The problem with phantom energy is that it does not just expand space, it completely dominates it. While normal dark energy allows galaxies to drift apart, phantom energy takes things to an extreme. It speeds up expansion so much that eventually nothing can resist it, not even the strongest forces in the universe. If phantom energy is real and continues to grow, then at some point in the far future, the universe will face the Big Rip. This terrifying event is not just about space expanding, it is about space expanding too much and too fast. Scientists predict that the Big Rip would happen in stages, gradually tearing apart different cosmic structures until nothing is left. Here's how it would unfold. 1 billion years before the Big Rip. At this stage, the expansion of the universe would be noticeable but not yet catastrophic. Galaxies would be moving away from each other at an increasing rate, but their internal structure would remain intact. However, the sky would look emptier over time as distant galaxies disappeared from view. 60 million years before the Big Rip. The effects of phantom energy would become much stronger. Galaxies that were once tightly held together by gravity would start breaking apart. Stars and planets within these galaxies would drift farther away from each other, like islands being separated by an ever-expanding ocean. 3 months before the Big Rip. At this point, the Milky Way galaxy, home to our solar system, would be ripped apart. The force of phantom energy would be so intense that even the powerful gravitational pull of black holes would no longer be enough to keep stars and planets together. The night sky would become unrecognizable, filled with only scattered stars drifting into emptiness. 30 minutes before the Big Rip. The destruction would now reach the level of individual planetary systems. The force holding planets in orbit around their stars would weaken, causing them to fly off into space. Even planets like Earth would no longer be safe as they are pulled away from the Sun. 1 second before the Big Rip. At this final stage, the effects would reach the atomic level. Molecules, atoms, and even subatomic particles would be stretched apart. The forces that hold electrons around an atomic nucleus would fail, and even the basic building blocks of matter would be torn apart. After this moment, nothing would remain. Space itself would be expanding so quickly that even the fabric of reality might be shredded. There would be no galaxies, no stars, no planets, and no atoms, only an empty, ever-expanding void. If the Big Rip is truly our universe's fate, is there anything we can do to stop it? Scientists are still unsure because phantom energy behaves in ways that do not follow the usual laws of physics. However, there are a few possibilities. Phantom energy might be temporary. Some scientists think that phantom energy could be a short-lived phase rather than a permanent force. If its effects slow down or reverse over time, the Big Rip might never happen. Instead, the universe might stabilize or change direction, preventing total destruction. A new physics could change everything. Our current understanding of physics is incomplete. There may be unknown laws or forces that could counteract phantom energy. Future discoveries in quantum mechanics or string theory might reveal a hidden balance in the universe that we do not yet understand. Escape to another universe. If the Big Rip is unavoidable, some theories suggest that intelligent civilizations might find a way to escape into another universe before their own is destroyed. This could involve traveling through wormholes, manipulating the fabric of space-time, or even creating artificial universes where life could continue. Right now, galaxies are already moving away from each other because of the universe's expansion. This has been happening for more than 13 billion years. However, gravity keeps galaxies together, preventing them from flying apart. If dark energy becomes more powerful over time, it will start to overpower gravity, and the first sign of the Big Rip would be galaxies drifting apart faster than ever before. Imagine looking up at the night sky and seeing fewer and fewer galaxies. Those beautiful clusters of stars that we see in telescopes today would become increasingly distant, their light stretching and fading as space itself expands. Over time, even the Milky Way, the galaxy that contains our solar system, would no longer be able to hold on to its closest neighbors like the Andromeda galaxy. Eventually, galaxies themselves would start to break apart. The stars that once swirled together in majestic spirals and glowing clouds of gas would no longer be held together by gravity. Instead, they would be flung apart into the expanding void. As the expansion accelerates, the next victims would be the stars themselves. Right now, stars are kept together by a delicate balance between gravity pulling inward and the pressure from nuclear reactions pushing outward. If dark energy becomes strong enough, it will break this balance. The forces holding stars together would weaken, causing them to swell, break apart, and eventually explode. Massive stars, like our Sun, would lose their ability to hold on to their outer layers, spilling their material into space. The glowing cores of these stars, which normally collapse into dense white dwarfs, neutron stars, or even black holes, might be torn apart before they can fully form. Black holes, which were once thought to be indestructible, could also be stretched and shredded as space itself expands faster than the speed at which even light can escape. Once the stars are gone, the planets orbiting them would be left exposed to the violent forces of expansion. With no gravitational anchor to hold them in place, planets would drift away from their dying stars. Moons, asteroids, and comets would also lose their orbits and be flung into the abyss. For Earth, this would be a horrifying event. Without the Sun's gravity, our planet would be sent spinning into the cold, empty darkness of space. The atmosphere would be stripped away, the oceans would freeze, and life would come to a tragic end. Other planets in our solar system, like Jupiter and Saturn, would experience the same fate. Eventually, all planets would be stretched apart, crumbling into dust as dark energy's grip tightens. As the universe's expansion reaches its final stage, even the smallest building blocks of matter, atoms, would not be safe. Atoms are made up of a nucleus containing protons and neutrons surrounded by electrons. These particles are held together by strong nuclear and electromagnetic forces. But if dark energy keeps growing in power, even these forces will not be able to resist it. Electrons would be torn away from their orbits and atomic nuclei would be pulled apart. The bonds that form molecules and chemical compounds would be shattered, meaning that even the fundamental elements of matter would cease to exist. This is the ultimate end, the moment when reality itself dissolves into a featureless void of individual scattered particles. At the very last stage of the Big Rip, even the fabric of space and time could be torn apart. The fundamental laws that govern physics might break down, and the very concept of distance and time could lose meaning. What was once a universe filled with galaxies, stars, and planets would become an infinite, empty expanse where nothing exists except isolated, individual particles. This event would happen incredibly fast in its final moments. Scientists estimate that in the last few seconds before the ultimate rip, everything that still exists, down to the tiniest particles, would be separated at faster than light speeds. Then, in an instant, it would all be over. The universe, once vibrant and full of wonders, would be nothing more than a vast emptiness with no structure, no time, and no possibility of rebuilding. While the Big Rip is a terrifying possibility, scientists are still unsure if it will actually happen. The fate of the universe depends on the nature of dark energy, which is still one of the biggest mysteries in physics. If dark energy remains constant over time, the universe will likely continue expanding forever, but at a slower rate, leading to a cold, dark future known as the heat-death scenario. However, if dark energy grows stronger, then the Big Rip becomes more likely. Astronomers are studying distant galaxies and cosmic background radiation to understand how dark energy behaves. Some theories suggest that dark energy might weaken over time, preventing the universe from ripping apart. Others suggest that new physics, beyond what we currently understand, might change our predictions entirely. Black holes are some of the most mysterious and powerful objects in the universe. They are like cosmic vacuum cleaners, pulling in anything that gets too close, including stars, planets, and even light itself. Their immense gravity makes them fascinating and terrifying at the same time. But what role do they play in the ultimate fate of the universe? Will they contribute to its destruction, Or will they be the last remnants of existence when everything else has faded away? To understand this, we must explore what black holes are, how they form, and how they might influence the long-term future of the cosmos. Let's take a journey through space and time to uncover the secrets of these dark giants and how they could shape the end of everything we know. A black hole is a region in space where gravity is so strong that nothing can escape from it, not even light. This happens because an enormous amount of mass is packed into a very small space, creating an intense gravitational pull. The boundary around a black hole, called the event horizon, marks the point of no return. Anything that crosses this invisible line is lost forever. Black holes are born when massive stars die. Stars shine by burning fuel, usually hydrogen, in a process called nuclear fusion. This fusion releases energy, which creates pressure that pushes outward, balancing the inward pull of gravity. However, when a star many times larger than our Sun runs out of fuel, it can no longer hold back the force of gravity. The star collapses under its own weight, and if it is massive enough, it will form a black hole. There are different types of black holes. Stellar black holes. These are formed when large stars die, and they usually have a few times the mass of our Sun. Supermassive black holes. These monsters exist at the centers of galaxies and can be billions of times heavier than our Sun. Intermediate black holes. These are in between stellar and supermassive black holes in size and are still a mystery to scientists. Primordial black holes. These tiny black holes might have formed right after the Big Bang, but they are purely theoretical at this point. No matter their size, all black holes have one thing in common. Once something falls in, it never comes out. But what does this mean for the future of the universe? Even though black holes are terrifying, they actually play an important role in shaping the universe. They influence their surroundings in several ways, controlling the growth of galaxies. At the center of nearly every galaxy, including our own Milky Way, there is a supermassive black hole. These gigantic black holes help regulate how galaxies grow. When a black hole consumes too much material at once, it releases powerful jets of energy. These jets can blow away gas and dust, slowing down the formation of new stars. In this way, black holes act as cosmic regulators, deciding when and where new stars can form. Creating extreme cosmic events. Black holes are responsible for some of the most violent events in the universe, such as gamma-ray bursts, some of the brightest explosions in the cosmos, which happen when a black hole forms. Gravitational waves, ripples in space-time caused when two black holes merge. Scientists on Earth can detect these waves with special instruments. Quasars. Some black holes consume so much material that they glow brighter than entire galaxies, forming objects called quasars. Recycling matter and energy. When black holes consume stars and gas, they don't always keep everything. Some of the material is ejected back into space in the form of powerful jets and radiation. This process can actually help create new stars and planets in different parts of the universe. However, while black holes can be creative forces, they also have the potential to play a major role in the ultimate fate of the universe. The universe is expanding. Galaxies are moving away from each other, and over time, space will become emptier and colder. This leads us to one of the biggest questions in physics. What will happen in the very distant future? Scientists have several theories about how the universe might end, and black holes play an important part in most of them. One of the most widely accepted ideas is that the universe will continue expanding forever until all the energy is spread so thin that no more stars can form and everything slowly fades to darkness. This is called heat death. In this scenario, black holes will be among the last objects left. All the stars will eventually burn out, and all matter may be swallowed by black holes. However, even black holes are not eternal. Over time, they slowly lose energy through a process called Hawking radiation, named after the famous physicist Stephen Hawking. Hawking radiation is incredibly slow. A black hole the size of our Sun would take trillions of years to evaporate, but eventually, even the largest supermassive black holes will disappear. This could take an unimaginable amount of time, far longer than the current age of the universe, which is about 14 billion years. When the last black hole finally vanishes, the universe will be a cold, empty place with nothing but faint traces of radiation. Another possibility is that gravity might eventually stop the universe from expanding, causing everything to collapse back together in a process called the Big Crunch. If this happens, black holes might merge into one giant black hole that consumes everything. Some theories suggest that this could lead to a big bounce, where the universe is reborn in a new Big Bang, starting the cycle over again. In another scenario, called the Big Rip, the universe's expansion speeds up so much that even atoms are torn apart. In this case, black holes wouldn't last forever because the very fabric of space-time would be ripped apart. Each of these scenarios depends on factors we don't fully understand yet, such as dark energy, the mysterious force pushing galaxies apart. Right now, we live in what scientists call the stelliferous era, a period where stars fill the universe, producing light and heat. This era began more than 13 billion years ago, shortly after the Big Bang. Today, stars come in different sizes and colors, from small, dim red dwarfs to massive, hot blue giants. These stars are born in giant clouds of gas and dust, live for millions or even billions of years, and eventually die. Massive stars explode as supernovae, leaving behind either neutron stars or black holes. Smaller stars, like our Sun, will expand into red giants before shrinking into white dwarfs, faint, dense remnants of their former selves. In about 100 trillion years, the last star in the universe will burn out. At this point, no new stars will be forming because most of the hydrogen, the fuel that powers stars, will be used up. During this time, the only objects left shining faintly will be white dwarfs, neutron stars, and black holes. White dwarfs will slowly fade into black dwarfs, cold, dark objects that no longer emit any light. The universe will become much darker, with only a few dimly glowing objects scattered across the vast emptiness of space. As time passes, even neutron stars will cool down, and the only truly active objects left will be black holes. These cosmic monsters, which formed from the collapse of massive stars, will slowly start consuming the remaining debris in space. After trillions upon trillions of years, the universe will enter a new phase, the black hole era. By this point, all stars will have disappeared, and only black holes will remain. These objects are so powerful that nothing, not even light, can escape their gravitational pull. They will become the most dominant structures in the universe. But even black holes are not immortal. Over time, they will slowly evaporate due to a strange process known as Hawking radiation, a theory proposed by physicist Stephen Hawking in the year 1974. According to this idea, black holes lose a tiny amount of energy over time as particles escape from their edges or event horizons. The smaller a black hole is, the faster it loses energy. The largest supermassive black holes, which are billions of times heavier than the Sun, will take an incredibly long time to disappear. More than 1 Google years, a number with 100 zeros. As black holes lose energy, they shrink and eventually vanish in a burst of energy. This process will take unimaginable amounts of time. For example, a small black hole with the mass of our Sun will take about 10 to the power of 64 years to evaporate. A supermassive black hole at the center of a galaxy will take even longer, possibly 10 to the power of 100 years or more. Once the last black hole disappears, the universe will be completely dark and empty. This is known as the heat death of the universe, a state where no energy remains to create new structures or life. The universe will become a vast, cold, and silent void. The black hole era will be a strange time, vastly different from the universe we see today. Here's what it might look like. A universe without light. With no stars left to shine, the cosmos will be completely dark. The only sources of radiation will be the faint glow of black holes slowly evaporating. Galaxies will be gone. Over immense timescales, galaxies will break apart due to gravitational interactions. Stars and planets that once orbited the centers of galaxies will be flung into deep space. Only black holes will remain, drifting alone in the vast emptiness. Matter will fall into black holes. Anything that remains in the universe, asteroids, dead planets, and even the last surviving particles, will eventually be pulled into black holes. As the universe continues to expand, the last remaining black holes will slowly shrink. When they finally vanish, the universe will be left in a state of true emptiness, with nothing remaining but cold, stretched out space. The future of the universe after black holes evaporate is uncertain. Some theories suggest that the universe will continue expanding forever in a state of complete emptiness. Others propose that quantum fluctuations might eventually trigger the birth of a new universe, a sort of cosmic reset that could start the cycle all over again. The process of black hole mergers happens in several stages. It is a long and complex journey, often taking millions or even billions of years. Let's break it down into simple steps. Most black holes that eventually merge start as two separate black holes orbiting each other. This usually happens when two massive stars, each at least 20 times the mass of the Sun, explode as supernovae. If these stars were already orbiting one another before they died, their remnants, now black holes, continue their cosmic dance. This system is called a binary black hole system. Over millions of years, the black holes slowly move closer together. This happens because they lose energy in the form of weak gravitational waves, tiny ripples in space-time, predicted by Albert Einstein's theory of relativity. As the black holes keep losing energy, they start spiraling toward each other faster and faster. Think of it like two figure skaters grabbing hands and spinning, except instead of a rink, they are warping the very fabric of space. During this phase, the black holes get so close that their speeds reach a significant fraction of the speed of light. The gravitational waves they emit become stronger, sending ripples across the universe. Scientists on Earth can detect these waves using special instruments like LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo. These instruments listen for the faint echoes of black hole collisions from millions or even billions of light years away. As the two black holes spiral closer, they eventually reach the final moment of their dance, the merger. In an instant, the two black holes collide, combining their masses into a single, even more massive black hole. The energy released during this moment is beyond comprehension. It is estimated that in just a fraction of a second, the merger can release more energy than all the stars in the observable universe combined. This energy is emitted in the form of extremely powerful gravitational waves, which ripple outward across the cosmos like shock waves from an explosion. After the violent collision, the newly formed black hole is not entirely stable at first. It wobbles and vibrates, like a bell that has just been struck. This stage is called the ring-down phase, and during this time, the black hole continues to release gravitational waves until it settles into a perfectly smooth, final form. Once the black hole stabilizes, it becomes quieter, but it remains a powerful force in the universe. Over time, it may grow even larger by consuming gas, dust, or even other black holes that drift too close. But why black hole mergers matter? Black hole mergers are not just mind-blowing cosmic events, they are incredibly important for science. Here's why. They prove Einstein was right. Albert Einstein predicted the existence of gravitational waves over 100 years ago, but they were not directly observed until 2015, when LIGO detected the first black hole merger. This confirmed that Einstein's theory of general relativity was correct. They help us understand space and time. When black holes merge, they create waves that stretch and squeeze space itself. By studying these waves, scientists can learn more about how gravity works and how space-time behaves under extreme conditions. They reveal hidden black holes. Some black holes are too far away or too dark to be seen with traditional telescopes. However, when they merge, their gravitational waves can be detected from across the universe. This allows scientists to discover black holes that would otherwise remain invisible. They might explain mysterious cosmic events. Black hole mergers could be linked to other mysterious space events, like powerful bursts of energy called gamma-ray bursts. Studying these mergers might help scientists unlock even more secrets of the universe. Since the early days of science, human beings have wondered what might happen when the universe ends. As our understanding of nature has grown, two powerful theories have emerged to explain the workings of the cosmos. On one side, there is general relativity, a theory developed by Albert Einstein in the early 20th century that tells us how gravity shapes the large-scale structure of space and time. On the other side, there is quantum mechanics, a set of ideas that describe the strange and unpredictable behavior of particles at the very smallest scales. Although each of these theories is remarkably successful in its own realm, they offer very different visions for what will happen when the universe reaches its final chapter. General relativity deals with the world on cosmic scales. It explains how stars, galaxies, and even the entire universe move under the influence of gravity. In this picture, space and time themselves are curved by mass and energy. General relativity predicts that the geometry of the universe can evolve in a dramatic way, possibly leading to events such as a big crunch or an endless expansion that cools into what is sometimes called heat death. In contrast, quantum mechanics governs the behavior of the tiniest pieces of nature, atoms, electrons, and even smaller particles. This theory is full of surprising ideas such as uncertainty, probability, and fluctuations that appear even in empty space. When we try to use quantum mechanics to predict the fate of the cosmos, we encounter possibilities that seem almost magical. Scenarios where random events, like sudden quantum jumps or vacuum collapses, might trigger a radical transformation of everything that exists. General relativity is a theory that explains gravity as a consequence of the curvature of space and time. In this framework, massive objects like stars and planets bend the fabric of the universe around them. When Einstein first published his ideas over 100 years ago, he transformed our understanding of how the cosmos works. One of the most striking predictions of general relativity is that the universe is not static, but expanding. Observations made by scientists such as Edwin Hubble, who discovered that distant galaxies are moving away from us, support this idea. The universe began in a hot, dense state and has been expanding ever since. How this expansion will continue is one of the key questions that general relativity helps us explore. General relativity tells us that the rate of expansion depends on the amount of matter and energy in the universe. If there is enough matter, gravity might eventually overcome the expansion and cause everything to collapse back together, a scenario known as the Big Crunch. In the Big Crunch, the universe would reverse its expansion, and all matter would be drawn into an ever-tightening ball, leading to conditions of extreme density and temperature that might mirror the beginning of the universe. This idea paints a picture of a cyclical universe, where each ending could potentially lead to a new beginning. Alternatively, if there is not enough matter to slow down the expansion, the universe might continue to stretch out forever. Over extremely long periods, trillions of years, the energy in the universe would become so thinly spread that stars would burn out and galaxies would drift apart. This slow fading into darkness is sometimes called heat death, because the universe would approach a state of maximum entropy, a condition in which no useful energy remains to do work. In this scenario, time itself would continue, but the universe would be cold and lifeless. Observations in the late 20th century added another twist to this picture. Scientists discovered that not only is the universe expanding, but it appears to be accelerating in its expansion. This acceleration is attributed to a mysterious force called dark energy, a form of energy that permeates all of space and works against gravity. In the framework of general relativity, dark energy could drive the universe to expand at an ever-increasing rate. If this trend continues, the universe might end in what is sometimes called the Big Rip. In the Big Rip scenario, the acceleration becomes so strong that it tears galaxies, stars, and eventually atoms apart. Every bound system would be ripped asunder by the overwhelming force of expansion. General relativity is a classical theory, meaning it does not include the effects of quantum mechanics. As a result, its predictions for the end of the universe are based on smooth, continuous models of space and time. These models are very useful for describing large-scale structures and events that involve huge amounts of mass and energy. However, as we approach conditions of extreme density and temperature, such as those near a black hole or at the very beginning of the universe, the predictions of general relativity begin to break down. The theory cannot account for the effects of quantum uncertainty or the small-scale fluctuations that occur in nature. Because of this, while general relativity gives us clear ideas about how the universe might evolve in scenarios like the Big Crunch, heat death, or Big Rip, it leaves unanswered many questions about what happens in the very final moments. How does space and time behave when densities become infinitely large? Can the laws of physics even be applied in such conditions? These questions are where quantum mechanics comes into play, offering a radically different perspective. Quantum mechanics is a theory that describes the world at the smallest scales, where particles do not behave in the predictable ways we see in our everyday lives. Instead of following precise paths, particles exist in states of probability, where only the likelihood of finding them in a certain place or state can be determined. This fundamental randomness is one of the hallmarks of quantum theory, and it leads to outcomes that seem counterintuitive compared to the smooth predictions of general relativity. At the heart of quantum mechanics is the principle of uncertainty. This principle tells us that it is impossible to know both the position and momentum of a particle with perfect precision. The more accurately one is known, the less accurately the other can be measured. This inherent uncertainty means that even empty space is never truly empty. Instead, it is a seething cauldron of tiny fluctuations, where particles and antiparticles continuously appear and disappear. These fluctuations are often referred to as quantum foam, and they hint at a universe that is far more dynamic and unpredictable at small scales than classical theories would suggest. When we consider the fate of the universe from a quantum mechanical perspective, these fluctuations become crucial. In a scenario called vacuum decay, for example, a tiny region of space could undergo a sudden shift in its vacuum state, a change in the lowest energy state of the quantum fields that fill space. If such a shift were to occur, it could trigger a chain reaction, transforming the very nature of the vacuum throughout the universe. This change might lead to conditions that are hostile to the structures and particles that currently exist, effectively ending the universe as we know it. Although this process is highly speculative and its likelihood is uncertain, it shows how quantum mechanics opens up possibilities that are entirely absent in the classical view. Another quantum phenomenon that comes into play when considering the universe's end is quantum tunneling. In the everyday world, particles usually need enough energy to overcome barriers, like a ball needing to be thrown over a wall. In the quantum world, however, particles sometimes tunnel through barriers, even when they do not have enough energy to climb over them. This means that, given enough time, even a seemingly stable system can change its state through random tunneling events. Some theories that try to bridge quantum mechanics with general relativity propose that instead of the universe ending in a singular catastrophe, such as a big crunch or big rip, it might undergo a quantum bounce. In this idea, when the universe contracts to an extremely small size, quantum effects could halt the collapse and cause a rebound, leading to a new expansion phase. In this picture, the end of one cosmic cycle is not the end of everything, but rather the beginning of another cycle. This scenario is sometimes called a cyclic universe, where the cosmos undergoes endless cycles of expansion and contraction. Although this idea is still very much under development, it illustrates how quantum mechanics can provide a very different and perhaps more hopeful vision of cosmic endings than the classical view. Quantum mechanics forces us to reconsider the very fabric of reality. In the realm of the very small, space and time may not be the smooth, continuous entities that general relativity describes. Instead, they might be discrete or quantized, meaning that there are smallest possible units of space and time. Some approaches to quantum gravity, a field that seeks to merge quantum mechanics with general relativity, suggest that space-time itself could have a granular structure. If space and time are not continuous, then the singularities predicted by general relativity, points of infinite density and zero volume, might be avoided entirely. This idea has important implications for the fate of the universe. If the catastrophic singularities that general relativity predicts are smoothed out by quantum effects, then the ultimate end of the universe might be less violent or final than once thought. Instead of ending in a sudden, singular explosion or implosion, the universe might transition more gently into a state that is hard for us to imagine with our current language and ideas. This possibility is one of the most exciting areas of research in modern physics, and it promises to reshape our understanding of everything from the Big Bang to the final fate of the cosmos. When we compare the predictions of general relativity and quantum mechanics, we are essentially looking at two very different ways of understanding the universe. General relativity deals with the grand stage of stars, galaxies, and the overall structure of space-time, where gravity reigns supreme. In contrast, quantum mechanics is concerned with the tiny actors on this stage, the particles that make up matter and energy, and the inherent randomness in their behavior. General relativity paints a picture of the universe that is smooth and predictable on large scales. It tells us that the fate of the cosmos is determined by the balance between the attractive force of gravity and the repulsive effects of dark energy. Depending on this balance, the universe might collapse back into itself, expand forever, or even tear itself apart. In all of these scenarios, the behavior of space and time is treated as continuous and well-behaved, even if it leads to extreme outcomes like a singularity. Quantum mechanics, on the other hand, shows us that at the smallest scales, the universe is far from smooth. Here, randomness and uncertainty dominate. Even in what we think of as empty space, there is a jittery, restless energy that gives rise to unpredictable events. This fundamental unpredictability means that the end of the universe could involve sudden, radical changes driven by quantum effects, changes that are not predicted by the smooth equations of general relativity. The real challenge comes when we try to apply both theories to situations where they are both important. The end of the universe, especially in scenarios that involve very high densities and extreme conditions, is one of those cases. For example, if the universe were to contract to a very small size in a big crunch, general relativity would predict a singularity, a point where the laws of physics as we know them break down. However, quantum mechanics suggests that when things get that small and energetic, the smooth fabric of space-time might instead be subject to wild fluctuations that prevent a singularity from ever forming. This clash is not just an academic curiosity, it points to a major problem in modern physics. Scientists have been trying for many decades to develop a theory of quantum gravity that would merge the smooth space-time of general relativity with the jittery, probabilistic world of quantum mechanics. Such a theory might finally give us a clear picture of what really happens when the universe meets its end. Until that time, we must live with two competing visions, one that is elegant and continuous, and another that is chaotic and full of surprises. Another area where these differences become clear is in the very nature of time. In general relativity, time is a dimension much like the dimensions of space. It flows in one direction and is intimately linked with the curvature of space. The end of the universe in a classical sense might involve time coming to a halt, as in a singularity, or stretching out endlessly in a slow, fading expansion. Quantum mechanics, however, suggests that time might not be as straightforward as we think. In some interpretations, time itself could emerge from more fundamental, timeless processes at the quantum level. This raises intriguing questions about what it means for the universe to end. If time is not a fixed backdrop, but a dynamic feature that can change under extreme conditions, then the end of the universe might not be a single moment in time, but a gradual transition that defies our usual understanding of beginnings and endings. The differences between general relativity and quantum mechanics become most pronounced when we consider the universe at its most extreme. For many scientists, this is the motivation behind the search for a unified theory that can bring together the best parts of both worlds. Two leading approaches in the quest for a theory of quantum gravity are loop quantum gravity and string theory. Loop quantum gravity tries to quantize space-time directly, suggesting that space is made up of tiny loops that form a kind of fabric. In this theory, the catastrophic singularities of general relativity might be replaced by a quantum bounce, a smooth transition from contraction to expansion. This idea offers hope that the universe might have a cyclic nature, with each cycle avoiding the brutal finality of a singularity. String theory, on the other hand, posits that the fundamental building blocks of nature are not point-like particles, but tiny vibrating strings. These strings can vibrate in many different ways, and each vibration corresponds to a different particle. String theory has the potential to unite all the forces of nature, including gravity, into a single framework. It also offers intriguing possibilities for the end of the universe. For example, in some versions of string theory, the vacuum state of the universe is not fixed, but can change through quantum fluctuations. Such changes could lead to entirely new universes being born out of the old, a process sometimes referred to as cosmic rebirth. Despite the promise of these approaches, a complete theory of quantum gravity remains elusive. The mathematics involved is extremely challenging, and many of the ideas remain speculative. However, the pursuit of such a theory is one of the most exciting areas of modern science. A successful theory of quantum gravity would not only explain the differences between the predictions of general relativity and quantum mechanics, but would also provide a much deeper understanding of the universe, from its fiery birth in the Big Bang to its final fate. Given the contrasting predictions of general relativity and quantum mechanics, what might the actual end of the universe look like? While we do not yet have a final answer, several intriguing possibilities emerge from our discussion. One possibility, largely emerging from general relativity, is that the universe will continue to expand forever. In this scenario, the energy in the cosmos will gradually be spread so thin that stars will burn out, galaxies will drift apart, and eventually no new stars will form. The temperature of the universe will slowly approach absolute zero, a state in which no energy remains to do any work. This is the so-called heat death of the universe. In a heat death scenario, the end is not a sudden event, but a very long, drawn-out process in which the universe becomes a vast, cold, and dark expanse. Another possibility is the Big Rip, which also finds its roots in general relativity, especially when dark energy is taken into account. If the mysterious dark energy continues to drive the acceleration of the universe's expansion, its effect might eventually become so strong that it tears apart galaxies, solar systems, and even atoms. In the Big Rip, the fabric of space itself is stretched to the point where nothing can hold together. This scenario envisions an ending that is both dramatic and violent, a final cosmic unraveling that happens all at once rather than gradually. From the perspective of quantum mechanics, however, the end of the universe might not be an ending at all. Instead, the universe could experience a quantum bounce. As the universe contracts under gravity, quantum effects might become strong enough to prevent a singularity from forming. At the moment when classical theories would predict a catastrophic collapse, quantum mechanics might instead cause a bounce, reversing the contraction and starting a new phase of expansion. This cyclic model suggests that the universe is caught in an endless loop of birth, death, and rebirth, a cosmic phoenix rising again and again from its own ashes. Yet another possibility arises from the inherent randomness of quantum mechanics: vacuum decay. In this scenario, the vacuum of space, that is, the state of lowest energy, might not be stable after all. Through quantum fluctuations, a tiny region of space could suddenly change its vacuum state, triggering a cascade that transforms the fundamental constants and particles of nature. If such a vacuum decay were to spread, it could alter the laws of physics across the entire universe, rendering it unrecognizable and hostile to any form of matter or life as we know it. The very different predictions of quantum mechanics and general relativity about the end of the universe highlight a major challenge in modern science. Each theory works incredibly well in its own realm, yet they seem to give us conflicting answers when we try to describe the most extreme conditions imaginable. This conflict is one of the central puzzles in physics today. Scientists have long hoped to find a theory that unifies general relativity and quantum mechanics. Such a theory would not only resolve the differences in predictions about the end of the universe, but would also provide a more complete understanding of nature itself. The search for quantum gravity is a journey into the unknown, where physicists are trying to understand how the universe operates at both the largest and smallest scales simultaneously. Whether through loop quantum gravity, string theory, or another approach that has not yet been discovered, the goal is to create a framework that can explain the evolution of the cosmos from the Big Bang to its ultimate fate. Beyond the technical challenges, the differing predictions of these theories have deep philosophical implications. They force us to ask what it really means for the universe to end. Is the end a sudden, dramatic event, or is it a gradual transformation that simply renders the universe unrecognizable? Could it be that there is no final end at all, but rather an eternal cycle of rebirth? These questions touch on our understanding of time, space, and even existence itself. The idea that the universe might experience a quantum bounce or undergo vacuum decay challenges our everyday notions of permanence and stability. In this long exploration, we have seen that the theories of general relativity and quantum mechanics provide two very different stories about how the universe might end. General relativity, with its smooth description of space and time, points us toward endings like the Big Crunch, heat death, or Big Rip. In these scenarios, the fate of the cosmos is tied to the balance of gravity, matter, and dark energy, a balance that shapes a universe that is either collapsing, slowly fading away, or tearing itself apart. Quantum mechanics, with its focus on the smallest scales, introduces an element of unpredictability and possibility. It tells us that even empty space is alive with fluctuations, that particles can tunnel through barriers, and that time and space might be far less continuous than they appear. These ideas lead to possibilities such as the quantum bounce, where the universe might avoid a catastrophic singularity by rebounding into a new phase of expansion, or vacuum decay, where a sudden change in the state of space itself could alter the laws of physics. What makes these theories so fascinating is that they force us to think about the end of the universe in entirely new ways. Rather than a single, inevitable fate, the end of the universe becomes a subject of deep uncertainty, a mystery that challenges our understanding of reality. The differences between the predictions of general relativity and quantum mechanics remind us that the cosmos is full of surprises and that our journey to understand it is far from complete. The search for a unified theory of quantum gravity is one of the most ambitious quests in science today. It is a journey that seeks to blend the elegant, continuous picture of general relativity with the wild, unpredictable realm of quantum mechanics. As scientists work to merge these ideas, they are not only trying to predict the fate of the universe, They are trying to uncover the fundamental nature of reality itself. In the meantime, the contrasting visions of a smooth, deterministic ending and a fluctuating, quantum-driven transformation continue to inspire debate and wonder. Whether the universe ends in a dramatic collapse, a slow fade into darkness, or a sudden shift that resets everything. The story of its end is one that reflects the deep mysteries at the heart of nature. One might say that the universe, in its grand narrative, does not have a simple conclusion. Instead, its ending might be as complex and layered as its beginning. Perhaps the end is not the final page, but rather a pause before a new chapter begins. The ideas of a cyclic universe, a quantum bounce, or even the possibility of multiple universes emerging from vacuum decay all suggest that the end of our universe might be a gateway to something entirely new, a cosmic rebirth that defies our everyday understanding of beginnings and endings. In this light, the tension between general relativity and quantum mechanics is not a problem to be solved, but a rich source of ideas that push the boundaries of science. It is a reminder that our understanding of the cosmos is always evolving, and that the mysteries of the universe continue to inspire scientists and philosophers alike. As we look to the future, the interplay between these two theories will likely lead to new discoveries that change our understanding of the universe once again. Whether it is through the slow, inevitable cooling of a universe in heat death, the sudden violence of a big rip, or the hopeful promise of a quantum bounce, the ultimate fate of the cosmos remains one of the most intriguing and profound questions in science. At the tiniest levels of existence, space is not empty. Instead, it is a chaotic sea of activity filled with quantum fluctuations. These are spontaneous and temporary changes in energy that occur everywhere in space, even in the vacuum of nothingness. Think of the quantum world like a pot of boiling water. The surface of the water is never completely still. It is always bubbling with energy, forming and collapsing tiny bubbles. Similarly, in the vacuum of space, energy bubbles in and out of existence due to quantum fluctuations. These fluctuations create particles and antiparticles that appear and then almost instantly annihilate each other. Even though this happens on an unimaginably small scale, it is a fundamental part of how our universe works. Quantum fluctuations are not just a theory, they have been observed in experiments. For example, the famous Casimir effect proves that even a vacuum is not truly empty, as virtual particles create tiny forces between objects in space. Now comes the fascinating question. If quantum fluctuations can create tiny particles, could they also create something much bigger, a new universe? The idea is based on the theory of cosmic inflation, which suggests that in the early moments after the Big Bang, the universe expanded at an unimaginable speed, growing exponentially in size. Some physicists believe that if a quantum fluctuation were to trigger a similar rapid expansion, it could create a new, self-contained universe. Imagine you are blowing up a balloon. If you blow hard enough, the balloon expands rapidly, growing into something much larger than before. Now, imagine that same principle, but applied to space itself. If a quantum fluctuation were to create a tiny, highly dense point with the right conditions, it might rapidly expand, forming a completely new universe separate from our own. This concept is connected to what scientists call the inflationary multiverse hypothesis. This theory suggests that our universe may not be the only one, but rather one of many that have emerged from different quantum fluctuations in an infinite cosmic sea. Each of these universes could have different physical laws, different particles, and even different dimensions of space and time. Many scientists propose that our own universe may have begun as a quantum fluctuation within some larger, unknown reality. According to this idea, before the Big Bang, there was no traditional space or time as we understand it. Instead, there was a state of quantum nothingness filled with random energy fluctuations. Then, one of these fluctuations could have grown large enough to trigger a runaway expansion, what we now call the Big Bang. Over time, this tiny fluctuation gave rise to all the matter, galaxies, stars, and planets that exist today. This idea aligns with certain interpretations of quantum mechanics and inflationary cosmology, suggesting that entire universes can emerge from what seems like empty space. But if this is true, it raises even bigger questions. If quantum fluctuations created our universe, could they create more universes in the future? Could quantum fluctuations explain why our universe has the particular laws of physics that it does? Does this mean that universes are constantly forming and disappearing beyond our reach? Another fascinating phenomenon in quantum mechanics is called quantum tunneling. This occurs when particles manage to pass through barriers that should, according to classical physics, be impossible to cross. Imagine a small ball sitting at the bottom of a hill. Normally, for the ball to get to the other side, it would need enough energy to roll up and over the hill. But in the quantum world, sometimes the ball can simply tunnel through the hill and appear on the other side, as if by magic. Some scientists believe that quantum tunneling could play a role in the creation of new universes. If certain conditions arise where energy fluctuations create a highly dense region, quantum tunneling might allow it to expand into a full-fledged universe. This is one of the ideas behind the false vacuum hypothesis, which suggests that our universe might exist in a temporary, unstable state. If it were to tunnel into a lower energy state, it could trigger the birth of a completely different universe, or even cause drastic changes to our own. Another area of research suggests that black holes might be linked to the birth of new universes. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape. At its center lies the singularity, a point of infinite density where the known laws of physics break down. Some physicists propose that when matter falls into a black hole, it could be compressed into a singularity and then repackaged into a new universe. In this scenario, the inside of every black hole could be the seed of another cosmos, completely cut off from our own. If this idea is correct, it means that our universe might itself be the interior of a black hole that formed inside an even larger universe. This would mean that black holes are not just destructive forces, but potential creators of new realities. Since the beginning of human history, people have wondered about the origins of the universe. From ancient times to today, we have tried to understand how everything came to be. As science has advanced, especially in the field of physics, our ideas about the universe have changed. In the past, people believed there was only one universe. But now, some scientists think there could be many universes, possibly even an infinite number of them. This idea is known as the multiverse. One of the most fascinating parts of this theory is the concept of bubble universes, separate universes that exist like bubbles floating in a vast cosmic sea. At the core of this idea lies the bubble universe theory. Imagine each universe as a soap bubble floating in an endless cosmic ocean. Some bubbles are large, some are tiny, and new ones are constantly forming. Our universe is just one of these bubbles, existing alongside countless others. Some may look like ours, with galaxies, stars, and planets, while others could be wildly different, perhaps governed by strange physics where time flows backward or gravity is far stronger than what we experience. But how did this idea come about? And what does it mean for our understanding of reality? To grasp this, we need to explore a theory known as eternal inflation. To understand the idea of eternal inflation, we first need to look at an important breakthrough in physics called cosmological inflation. This theory, introduced by physicist Alan Guth in the 1980s, aimed to solve some of the biggest mysteries about the early universe. Scientists realized that our universe had to go through an incredibly rapid expansion right after the Big Bang. This super-fast growth, called inflation, explains why the universe looks so smooth and uniform, with galaxies evenly spread out instead of clumped together in chaos. But while inflation was originally thought to be a brief event in cosmic history, some scientists took the idea even further. This is where eternal inflation comes in. Instead of stopping after a short burst, this version of the theory suggests that inflation is still happening, just not everywhere at once. Some regions of space continue to expand at an unimaginable speed, while others, like our universe, settle down and begin forming stars and galaxies. The parts that keep inflating eventually break off, creating new bubbles, each one a separate universe with its own unique fate. Picture the vast expanse of the cosmos as a bubbling pot of boiling water. The water represents space, while the bubbles that form and rise are different universes popping into existence. Each bubble universe forms when inflation in a particular region of space suddenly slows down. This happens through a quantum process called quantum tunneling, which sounds complex but can be simplified. Imagine a ball sitting on top of a hill. Normally, it would need to roll down to reach the bottom. But in quantum mechanics, things don't always work the way we expect. Instead of rolling, the ball could magically teleport to the bottom of the hill. This is called tunneling. Something similar happens in the inflating regions of space. A small part of space experiences a sudden drop in energy, creating a hot and dense environment. This is the birth of a new universe. Within this bubble, time and physics unfold in a way that might be similar to our own. Just like our universe started with the Big Bang, each bubble universe could begin with its own Big Bang, expanding and evolving separately. If we truly live in a multiverse, what might the other universes be like? The possibilities are endless. Universes similar to ours. Some bubble universes might be nearly identical to our own. They could have the same laws of physics, similar galaxies, and even planets that look like Earth. In fact, if the multiverse is infinite, there might be countless versions of you, living slightly different lives in parallel realities. Universes with different physical laws. Some universes might have completely different laws of physics. Maybe gravity is stronger or weaker. Maybe atoms don't form the same way, meaning stars and planets never take shape. Some universes could be dark, lifeless voids, while others might be filled with strange new types of matter. Universes where time works differently. What if time flowed backward in another universe? In some theories, certain bubble universes could experience time in reverse, where the future is already set and the past is something yet to happen. Imagine a world where people grow younger instead of older. Some scientists speculate that certain universes might exist purely as mathematical structures, no physical matter, just patterns of energy or information. While this sounds bizarre, some theories suggest that our own reality might be based on mathematical principles at its core. The idea of traveling between universes is a popular concept in science fiction, but is it actually possible? Right now, we have no way of reaching another universe. The boundaries of each bubble universe act as an invisible barrier, separating them from one another. Even if we could somehow get close to the edge, the physics of our universe might not work in the next one. It would be like a fish trying to survive in outer space, completely incompatible with the environment. However, some scientists speculate that wormholes, hypothetical tunnels through space-time, could act as shortcuts between universes. If these wormholes exist and we could learn to harness them, inter-universal travel might not be impossible. While the idea of multiple universes is fascinating, it's still just a theory. Unlike black holes or galaxies, we can't directly observe other universes. However, there are clues that hint at the possibility. For example, some scientists believe that unusual patterns in cosmic background radiation, the faint glow left over from the Big Bang, might be evidence that our universe once collided with another bubble universe. Others argue that certain quantum mechanics experiments suggest our reality is just one of many possibilities. Until we find concrete proof, the multiverse remains one of the greatest scientific mysteries. You might wonder, why should we care about other universes if we can't even reach them? The answer lies in our never-ending quest to understand reality. If the multiverse exists, it changes everything we thought we knew about existence. It means our universe is not special or unique, it's just one of countless others. It also raises deep philosophical and scientific questions. If there are infinite universes, does that mean infinite versions of ourselves exist? Are there universes where different choices led to different outcomes? Could our understanding of physics be just one perspective among many? The search for the multiverse challenges us to think beyond what we see and pushes the boundaries of human knowledge. Whether or not we ever find proof, exploring these questions expands our understanding of the cosmos and our place within it. If the Big Crunch happens, it could lead to a new Big Bang. This idea is called the cyclic universe theory. It suggests that the universe goes through endless cycles of expansion and collapse. Each time the universe ends, a new one is born, just like a phoenix rising from its ashes. But how could this happen? If everything collapses into a single point, the enormous pressure and temperature might trigger another massive explosion, restarting the cycle. Some scientists think that this has already happened many times before, meaning our universe might not be the first one. Scientists have studied cosmic background radiation, energy left over from the original Big Bang, to understand how the universe evolved. Some unusual patterns in this radiation have led researchers to question whether past universes left behind traces. However, there is no definite proof yet. Another idea comes from quantum mechanics, which studies tiny particles that make up everything in the universe. Some theories suggest that when the universe shrinks into a tiny point, quantum forces could push it outward again, leading to a new Big Bang. If another Big Bang were to happen, the new universe might look completely different from ours. The laws of physics, time, and space could be different. New types of matter might form, and even time itself might work in ways we cannot understand. Alternatively, the new universe could be similar to ours, with galaxies, stars, and possibly even life. Some scientists believe that if a new universe forms, it could be shaped by the remnants of the previous one, meaning some aspects of our universe might survive in a new form. If a new Big Bang occurs, it would mean that everything we know, including our galaxy, our planet, and even ourselves, would be completely wiped out. However, since this process would take billions of years, humans might not even be around to witness it. Some scientists wonder if advanced civilizations in the distant future could find a way to escape the end of the universe and continue existing in a new one. While this is purely speculative, it raises fascinating possibilities about the nature of life and existence. Imagine a universe where everything has ended. The stars have burned out, galaxies have drifted apart, and even the tiniest particles have decayed into nothingness. What happens to time in such a universe? Does it continue to flow, or does it stop altogether? The idea of time in a dead universe is a profound and complex topic that challenges our understanding of reality itself. Time is something we experience every day, but defining it is not so simple. It is often described as the continuous flow of events from the past, through the present, and into the future. In physics, time is a fundamental part of the universe, closely linked with space in what scientists call space-time. This idea was made famous by Albert Einstein, whose theory of relativity showed that time is not fixed. It can stretch, shrink, and even slow down under different conditions. But time does not exist on its own. It is tied to movement, energy, and change. We measure time by observing how things move and transform, like the ticking of a clock, the rotation of the Earth, or the burning of a star. So, if the universe were to reach a state where nothing changes anymore, would time still exist? To understand time in a dead universe, we must first understand how the universe evolves. Scientists believe that our universe began approximately 13,800,000,000 years ago in an event known as the Big Bang. This was a moment of unimaginable energy, where space, time, and matter all came into existence. Since then, the universe has been expanding. Stars formed, galaxies took shape, and planets, including our own Earth, came into existence. Over billions of years, stars burned their fuel, exploded as supernovae, and gave birth to new stars. But this process will not continue forever. Eventually, the universe will reach a point where all sources of energy are used up. Scientists have proposed several possible endings for the universe. The most widely accepted scenario is called the heat death, or the Big Freeze. In this scenario, the universe continues to expand forever. As it expands, galaxies move farther apart and stars slowly burn out. Over trillions of years, even the smallest embers of light will fade away. Without energy, without heat, without movement, only cold darkness will remain. Another theory suggests that the universe might collapse in on itself in an event called the Big Crunch. In this case, gravity would eventually pull everything back together, reversing the expansion and crushing everything into a single point. This might lead to another Big Bang, starting the cycle all over again. But let's assume the heat death happens. The universe goes completely dark and lifeless. What does this mean for time? The biggest question in this discussion is whether time continues to exist if nothing is happening anymore. If time is tied to change and movement, what happens when everything stops moving? One way to think about this is to consider what it means to measure time. Today, we measure time by observing movement, whether it is the ticking of a clock or the movement of the Earth around the Sun. If there were no more clocks, no more moving planets, and no more active particles, would there still be a way to measure time? Some scientists believe that in a dead universe, time would still exist, but it would become meaningless. Imagine being in a dark, empty room with no sound and no movement. How would you know whether a second, a minute, or an hour had passed? Without change, time loses its purpose. Others argue that time itself might come to an end. Some theories suggest that time is not a fixed thing, but rather something that emerges from the activity of the universe. If the universe reaches absolute stillness, time might simply cease to be. Before the universe reaches total heat death, one last force might remain active for an extremely long time: black holes. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. When large stars die, they sometimes collapse into black holes, which then slowly consume matter and energy from their surroundings. Even in a universe where all stars have gone out, black holes will still be present. However, black holes do not last forever. Over an unimaginable period, estimated to be one followed by 100 zeros years, known as a Google years, black holes will slowly lose energy through a process called Hawking radiation. Eventually, even the largest black holes will vanish, leaving behind nothing but a thin, cold mist of subatomic particles. At this stage, the universe will be completely dark and empty. No stars, no black holes, no movement. The last traces of energy will be stretched thin, scattered across an infinite void. This is what scientists call the Dark Era, the final stage of the universe's existence. If time stops in a dead universe, is there any way for it to begin again? Some theories suggest that even in complete emptiness, strange quantum events could still occur. Quantum mechanics is the branch of physics that deals with the behavior of the smallest particles in existence. It suggests that particles can sometimes appear and disappear randomly. Some scientists believe that, given an infinite amount of time, a random fluctuation in energy could create a new Big Bang, starting a brand new universe from scratch. This idea suggests that our universe might be just one in an endless cycle of universes, each one born, living for billions or trillions of years, and then fading into silence before a new one emerges. If this is true, time never really ends. It just resets over and over again. As humans, our experience of time is deeply personal. We measure our lives in seconds, minutes, hours, days, and years. We see time as something that moves forward, never backward. But the idea that time could stop or restart challenges everything we know. If we could somehow observe a dead universe, would we experience it as an endless moment of stillness? Would it feel like time had simply vanished? Or would time still tick forward even if nothing changed? From the moment we are born, we start experiencing time through changes around us. The sun rises and sets. Babies grow into children, then teenagers, then adults. Leaves turn from green to orange to brown, then fall to the ground. The human brain is wired to recognize patterns, cycles, and differences. This is how we perceive time. Imagine for a moment that you wake up one day and absolutely nothing has changed. The clock on your wall remains frozen at the same hour, minute, and second. The people around you do not move. The air does not stir. You do not feel hunger, tiredness, or any need to do anything. Days do not turn into nights because the sun remains in one place. Would you still feel that time is passing? If there is no change, there is no way to measure time. Our minds might still be aware, but without any difference to mark the passage of moments, it would feel as if time had stopped. This suggests that time, at least as we experience it, is deeply connected to change. Scientists have long debated whether time is something real or just a concept humans use to make sense of the world. According to the famous physicist Albert Einstein, time is not absolute, it is relative. His theory of relativity, published in the early 20th century, showed that time can slow down or speed up depending on how fast you are moving and how strong the gravitational pull is around you. For example, astronauts on the International Space Station experience time slightly differently than people on Earth. Because they are moving at high speeds around the planet, time passes a tiny bit slower for them than it does for us on the ground. If they spent many years in space, they would age slightly less than their friends and family on Earth. But what happens if there is no movement at all? If everything in the universe became completely still, with no particles vibrating, no light traveling, and no forces acting on anything, what would happen to time? Some scientists argue that time would no longer have any meaning. If there is nothing to change, then there is nothing to compare one moment to another. It would be as if time had stopped. Others believe that time is a fundamental part of the universe, existing even if nothing happens. They argue that time is like a background fabric, always present, even if it is not being used or measured. In this view, time is an independent reality, not just a human perception. Another fascinating idea is that time might not just stop, it could loop. Some scientists and philosophers have suggested that instead of moving in a straight line from the past to the future, time could be circular. This would mean that instead of history continuing forward forever, it might repeat itself in an endless cycle. Imagine that the universe goes through phases of expansion and contraction. It grows for billions of years, then collapses back into a tiny point, only to explode outward again in another Big Bang. If this happens, history might repeat exactly as it did before. You might be reading this same sentence in another version of reality, countless times over. In such a loop, everything that has ever happened would happen again, exactly as before, with no one aware that they are reliving the same moments. Would time still have meaning if the future was always the past repeating itself? Some theories suggest that even if time loops, small changes might occur. Perhaps slight differences emerge each time the cycle repeats, meaning that no two versions of reality are exactly the same. If that is true, time would still be meaningful because change, no matter how small, would still exist. Beyond science, philosophers have explored whether time is real or simply a product of human consciousness. If no one was alive to experience time, would it still exist? Some argue that time is just a way for humans to make sense of existence. If nothing changes and no one is there to notice, does time matter at all? Imagine a deep, dark cave where nothing ever moves, no sound exists, and no creatures live. If a clock were placed inside, would time still pass? Scientifically, we would say yes, because outside the cave, the universe is still changing. But what if all of existence was like that cave, frozen, silent, and unchanging? Some philosophers suggest that in such a reality, time itself would vanish. Others argue that time is an independent force that does not need human perception to exist. They claim that even if no one can measure it, time continues because it is a property of the universe, just like space. This means that even in a completely frozen world, time would still be there, even if no one could tell. If nothing ever changed, life as we know it would not be possible. Our entire existence depends on movement, growth, and transformation. The Earth orbits the Sun, allowing for days, nights, and seasons. Our bodies function through countless tiny changes. Our hearts beat, our cells renew, our thoughts form and shift. Without change, all of these would stop, and reality itself would become unrecognizable. If time lost its meaning, what would that imply for us? Would we still be aware? Would our consciousness exist in a timeless state? Some people believe that this could be similar to deep sleep or even death, an existence without awareness, where time does not matter because there is no mind to perceive it. On the other hand, if time is simply a human invention, then perhaps its loss would not affect the deeper reality of the universe. Instead, everything would just be, without past, present, or future. It is a difficult idea to grasp because everything we know is based on time's passage. The simulation hypothesis is the idea that everything we see, feel, and experience in life might not be real, but instead part of a highly advanced simulation, something like a giant computer program in which we ourselves are just digital creations. This concept has sparked intense discussions among philosophers and scientists, as well as in the world of technology. In the year 2003, philosopher Nick Bostrom introduced what he called the simulation argument. He suggested that if a civilization advanced enough to create conscious beings inside a simulation, it would likely create an enormous number of them. If that were true, then the odds of any random conscious being, like you or me, actually living in the real world would be extremely low. Instead, we would almost certainly be living inside one of those simulations. Bostrom's argument presents three possible scenarios, known as a trilemma. Advanced civilizations never create simulations, either because they destroy themselves before reaching that stage, or because the technology proves impossible to develop. Advanced civilizations choose not to create simulations, perhaps due to ethical concerns or a lack of interest. If civilizations do create simulations, then the number of simulated beings would far exceed real ones, meaning we are almost certainly living in one. This idea assumes that consciousness is not limited to biological brains. In other words, if the right kind of computational system is created, it could think and feel just like a human. While the idea of a simulated world may sound futuristic, the question of reality versus illusion has fascinated thinkers for thousands of years. Many ancient philosophies explored the idea that the world might not be what it seems. The Chinese philosopher Zhuangzi once dreamt he was a butterfly, and then wondered if he was actually a butterfly dreaming he was a man. In Indian philosophy, the concept of Maya describes the world as an illusion that masks a deeper truth. Ancient Greek philosophers, such as Anaxarchus and Monomus, compared reality to a painted scene or a dream, suggesting that what we see might not be real. The Aztecs believed the world was like a book or a painting written by a divine force known as Teotl. Perhaps the most famous example in Western philosophy is Plato's Allegory of the Cave, written in the 4th century BCE. Plato described people who had spent their whole lives chained inside a dark cave, only able to see shadows on the wall. To them, the shadows were reality. But in truth, a greater world existed outside the cave, one they had never seen. This story suggests that our understanding of reality might be just as limited. Fast forward to the 17th century, and philosopher René Descartes proposed an idea that shook the foundations of philosophy. He imagined that an evil demon might be controlling all of his perceptions, making everything he saw and felt an illusion. This concept later evolved into the famous brain in a vat thought experiment, where a brain, connected to a supercomputer, would experience a completely artificial reality, without ever realizing it. In the 20th century, the idea took a scientific turn. In 1969, the German scientist Konrad Zuse published a book called Calculating Space, in which he suggested that the entire universe might operate like a vast computational system, an idea that later became known as digital physics. Bostrom's argument does not outright claim that we are living in a simulation. Instead, it says that one of these three things must be true. Almost no civilization ever reaches a highly advanced stage. Advanced civilizations choose not to create ancestor simulations. If simulations exist, most conscious beings in the universe are simulated. If the third scenario is correct, it would mean that nearly everyone who has ever lived, including us, exists inside a simulation rather than in a real, physical world. Bostrom argues that if future civilizations are capable of creating realistic simulations and have no restrictions or ethical concerns about doing so, then it would be extremely unlikely that we are among the few real beings in the universe. Instead, we would be part of a much larger population of simulated beings. The question then becomes, if we are living in a simulation, how could we ever know? Some scientists and researchers have even proposed tests to detect glitches or patterns that might reveal the underlying code of our reality. The idea that humans might be living in a simulation is not entirely impossible to prove. Philosopher Nick Bostrom even imagines a scenario where a message suddenly appears on a screen stating, "You are in a simulation. Click here for more information." However, if reality were simulated, its flaws might be too subtle for its inhabitants to notice. To maintain the illusion, any memory of such a revelation could even be erased by the system running the simulation. Still, if solid evidence were ever found, either confirming or disproving the theory, it would completely change how people view the probability of living in a simulated world. Bostrom takes the idea further than traditional skeptical theories. He argues that there are real-world, scientific reasons to believe one of three possibilities must be true. Human civilizations never reach a highly advanced stage because they go extinct first. Advanced civilizations do exist, but for some reason, they choose not to create realistic ancestor simulations. Advanced civilizations do run such simulations, and if they do, we are almost certainly living inside one right now. Bostrom does not claim to know which of these three possibilities is true. He notes that different people tend to pick different answers as the obvious one. Some believe humanity is doomed to extinction, option 1. Others think civilizations just are not interested in running simulations, option 2. And still, others feel it is most likely that we are inside a simulation, option 3. According to him, unless we are currently inside a simulation, then future civilizations will almost certainly never create ancestor simulations at all. Some philosophers challenge Bostrom's argument, questioning whether beings inside a simulation would even be conscious. If simulated humans are not truly self-aware, then the argument loses some of its weight. Others propose that humans could naturally sense that they are real and not just computer-generated entities. Philosopher Barry Dainton offers a modified version of Bostrom's argument. He suggests that rather than ancestor simulations, the real concern should be high-tech neural simulations. These could range from brains in a vat, where a person's brain is kept alive and fed artificial experiences, to future humans who are made to believe they are living as their distant ancestors. If such neural simulations were created with extreme accuracy, then the people inside them would not be able to tell the difference between reality and illusion. If that is true, then one of two things must be correct. Either almost no civilizations reach the point of running such simulations, or we are already in one. Many scientists remain unconvinced. Physicist Sabine Hossenfelder argues that simulating an entire universe without introducing glitches or inconsistencies is physically impossible. She dismisses the simulation theory as pseudoscience and compares it to religious belief. Cosmologist George Ellis is equally critical, stating that the idea is unrealistic from a technical standpoint and more suitable for late-night pub discussions than serious scientific inquiry. Some critics believe the simulation could still be in its first generation, meaning that all the simulated people expected to exist in the future have not been created yet. This perspective aligns with philosophical presentism, the belief that only the present moment truly exists. Physicist Sean Carroll points out a contradiction in the simulation hypothesis. If most humans throughout history are simulated, but humans are incapable of running simulations themselves, then it makes no sense to assume that other civilizations must have already built them. Another physicist, Frank Wilczek, notes that the laws of physics contain unnecessary complexities that would not be needed in a simulation. He also raises a fundamental question. If our world is simulated, then what is the world outside the simulation made of? If we are in a digital universe, what laws govern the system running the simulation? This, he argues, leads to an endless cycle of unanswered questions. Brian Eggleston argues that future humans within our universe could not be the ones running the simulation, because our universe itself is supposed to be the one being simulated. In other words, the probability of living in a simulation depends on whether other universes exist in the first place. Some scientists believe that, based on Bostrom's logic, one of the first two possibilities must be correct. Either humans do not survive long enough to create ancestor simulations, or advanced civilizations simply do not make them. Physicist Paul Davies even uses this idea to argue against the idea of a near-infinite multiverse. He reasons that if an infinite number of universes existed, then at least some of them would contain post-human civilizations running simulations. But if that were true, then the conclusion that we are in a simulation would become too absurd to accept, and so, by reductio ad absurdum, the idea of a vast multiverse is likely false. Right now, there is no evidence that technology capable of creating such high-fidelity simulations exists. Furthermore, we do not know if it is even possible for an advanced civilization to create such a simulation. Some scientists argue that until there is proof, we should assume the first possibility is true, that no civilization ever reaches the point of building realistic ancestor simulations. Additionally, there are fundamental limits to how much information a computer can process, meaning that even a highly advanced civilization might not have enough computing power to simulate an entire universe in perfect detail. Physicist Marcelo Gleiser strongly disagrees with the idea that highly advanced beings, so-called post-humans, would have any reason to create simulated universes. He argues that by the time they reach such a level of intelligence, they would already know enough about their past and would likely have little interest in running full-scale simulations of history. Instead, they might create virtual reality museums where they could step into the lives of their ancestors and experience their struggles firsthand. However, Gleiser sees the idea of a complete, resource-draining simulation of an entire universe as a massive waste of time. He also highlights a major issue. If such simulations exist, there's no reason to think they would stop at just one level. The simulated beings could, in turn, create their own simulations, leading to an endless loop, similar to the classic philosophical question of the first cause, which asks what started everything in the first place. In the year 2019, philosopher Preston Green proposed a startling idea. If we are indeed living in a simulation, it might be better not to find out. He worried that if we somehow proved our reality was artificial, those controlling the simulation might shut it down, bringing everything to an abrupt end. Economist Robin Hanson takes a different approach, suggesting that if we are in a high-quality simulation, it might be in our best interest to behave in a way that pleases those running it. Otherwise, we risk being deleted or moved into a lower quality simulation where we would be less aware and less conscious. Hansen even speculates that if someone truly believed they were living in a simulation, they might start caring less about long-term plans and the well-being of others. He explains that if a person knew they would never actually retire, or that certain places, such as Ethiopia, only existed within the simulation, then they might lose motivation to save money for the future or help people in need. Beyond simply debating whether the simulation hypothesis is true, philosophers have used the idea to explore other deep questions in metaphysics and knowledge theory. Philosopher David Chalmers has suggested that simulated beings might wonder if their thoughts and mental experiences are shaped by the physics of their world, when in reality, their consciousness could be running separately from the simulated universe. If this were the case, their thoughts wouldn't actually be caused by the rules of physics within the simulation. Chalmers argues that this idea challenges the common belief that mind and body must always be connected, a view known as Cartesian dualism. While he does not fully support dualism, he believes it is not as problematic as some claim. Similar arguments have been made regarding personal identity, questioning whether someone could have been an entirely different person in the past. Other arguments explore how we perceive things, such as colors, suggesting that our experiences of color could have been completely different if our minds were wired differently to the simulated world. A related concept is computationalism, a theory in the philosophy of mind that suggests thinking is essentially a form of computation. This theory is important to the simulation hypothesis because it explains how a simulated world could contain conscious beings, so-called virtual people. Since we know that physical systems can be accurately simulated to a certain extent, computationalism suggests that if consciousness can be created artificially, then a simulated reality with self-aware individuals is theoretically possible. However, this idea is still highly debated. Some argue that consciousness might require something more than computation, something that computers simply cannot replicate. If this is true, then even if humans behave as if they are conscious in a simulation, they may actually be what philosophers call zombies, entities that act alive but lack true awareness. If human consciousness cannot be simulated, then Nick Bostrom's famous simulation argument loses its foundation. However, this does not rule out the idea that humans could be brains in a vat, meaning that even if true consciousness cannot be simulated, humans could still be real, self-aware beings trapped inside an artificial world. Some theorists have taken this argument even further. If the idea that consciousness is just computation is correct, and if mathematical realism, the belief that mathematical structures truly exist, is also true, then consciousness could exist on any computational platform, including within a simulation. This would mean that consciousness is not tied to any one physical form and could be simulated like any other mathematical function. Futurist Hans Moravec has explored this idea, even suggesting that every physical object, including something as simple as a rock, could, in theory, be carrying out every possible computation, meaning that reality itself might already be a vast mathematical simulation. These ideas raise profound questions about the nature of existence, the limits of technology, and whether our reality is truly what it seems, or just an illusion created by something far beyond our understanding. In the world of physics, some scientists see the universe not just as a collection of stars, planets, and galaxies, but as a massive system that processes information, like a gigantic computer. This idea was first noticed by physicist John Archibald Wheeler. Over time, two main viewpoints emerged. The first suggests that the universe itself functions like a quantum computer, constantly calculating and processing data. The second proposes that our universe is actually a simulation, meaning that something or someone outside of it is running the program that creates everything we see. One expert in quantum computing, Dave Bacon, raised an interesting point about this idea. He noted that we live in an era where computers and information technology are everywhere. Because of this, people might be naturally inclined to think of everything in terms of computation, even when it comes to the laws of physics. However, he also pointed out a major issue. No one has ever found solid proof that our universe operates like a digital system the way computers do. There are no clear signs of the kind of small, separate units of information, like computer bits, that would be expected if reality were digital. So far, no predictions made by supporters of this idea have been confirmed through experiments. In the year 2012, 3 physicists, Silas Bean, Zoe Davudi, and Martin Savage, came up with a way to test one version of the simulation theory. Their idea was based on the fact that any simulation would have limits, just like a computer program can only handle so much data before it slows down or crashes. If our universe were simulated, the program running it would need to break space and time into tiny, separate points rather than allowing for a smooth, continuous reality. This could lead to effects we might be able to observe. One possible sign of this, they suggested, could be found in cosmic rays, high-energy particles from space. If these rays were distributed in an unusual, uneven way, it might be evidence that we live in a simulated world. In the year 2017, another team of scientists led by Tom Campbell proposed several different experiments to test the simulation theory. They believed that, with the right approach, it might be possible to find glitches or inconsistencies in our reality that would point to the existence of an underlying computer program. Some well-known figures have also weighed in on this debate. In a 2018 interview with NBC News, astrophysicist Neil deGrasse Tyson said that he believed the odds of us living in a simulation were better than 50-50. He admitted that he couldn't come up with a strong argument against it. However, in a later discussion with his friend J. Richard Gott, a professor from Princeton University, he encountered a thought-provoking counterargument. Gott pointed out that if simulated universes can create other simulated universes, then we would expect to see that happening in our world. But since humanity has not yet developed the technology to create high-quality simulated universes, there are only 2 possibilities. Either we are in the original, real universe, meaning no simulated worlds exist yet, or we are one of the very last in a long chain of simulations. This second possibility is unlikely, making the simulation theory seem much less probable to Tyson. He even admitted that this argument changed the way he thought about the entire subject. Elon Musk, the famous entrepreneur behind Tesla and SpaceX, has been one of the strongest supporters of the simulation hypothesis. In various interviews and press conferences, he has argued that as video game technology improves, we will eventually reach a point where virtual worlds become completely indistinguishable from reality. In a 2016 interview, he even estimated that there is only a 1 in 1 billion chance that we are living in the base reality, the original, non-simulated universe. Instead, he believes it is almost certain that we are living in a computer-generated world created by beings far more advanced than us. Rizwan Virk, an expert from the Massachusetts Institute of Technology and author of the simulation hypothesis, has also explored this idea. He shared a personal story that made him question reality. One day, while using a virtual reality headset, he became so immersed in the digital world that he forgot he was standing in an empty room. This moment made him wonder, if a simple headset can make us forget the real world, could it be possible that our entire reality was designed by a more technologically advanced civilization? The idea that reality might not be what it seems is not new. It has been debated by philosophers for thousands of years. The ancient Chinese philosopher Zhuangzi famously told the story of the butterfly dream. One night, he dreamed that he was a butterfly, happily fluttering about. But when he woke up, he was Zhuangzi again. This left him wondering, was he a man who had dreamed of being a butterfly, or was he actually a butterfly now dreaming that he was a man? This ancient thought experiment raises the same fundamental question as the simulation theory. How can we be sure that our experiences are real? Similar ideas also appear in Indian philosophy. where the concept of Maya suggests that the physical world is an illusion. Ancient Greek philosophers, such as Anaxarchus and Monimus, compared life to a painting or a dream, suggesting that everything we experience might not be real. The 17th century philosopher René Descartes famously stated, "It is possible that I am dreaming right now and that all of my perceptions are false." He argued that since dreams can feel just as real as waking life, we can never be fully certain that we are not dreaming at any given moment. In modern philosophy, David Chalmers has explored the dream hypothesis and proposed two versions of it. The first suggests that we are simply dreaming right now, meaning many of our beliefs about the world are incorrect. The second, more extreme version suggests that we have always been dreaming, that everything we have ever experienced exists only in our imagination. Some philosophers, like Ludwig Wittgenstein, reject these skeptical ideas altogether. Wittgenstein believed that questioning reality to such an extreme degree was pointless because we need some basic assumptions about the world to even make sense of such discussions in the first place. Beyond philosophy, even literature and mythology have explored similar ideas. The Aztecs described the world as a painting or a book created by a divine force called Teotl. Friedrich Nietzsche, in his book Beyond Good and Evil, criticized the idea that there is a true reality hidden behind the world we experience. He suggested that perhaps everything we believe to be real is just a fiction, and that truth itself is just a human invention. For centuries, scientists have worked to uncover the fundamental building blocks of the universe. Atoms were once thought to be indivisible, but discoveries in the 20th century revealed that atoms are made up of even smaller particles: protons, neutrons, and electrons. While electrons are fundamental particles that do not break down into smaller components, protons and neutrons are made of even tinier particles called quarks, held together by powerful forces. Protons are widely believed to be stable, meaning they do not decay or break apart over time. However, some theories in modern physics suggest that protons might not be eternal. If protons do decay, the implications would be enormous, changing our understanding of matter and the very foundation of physics. But what exactly happens when a proton decays, if it does at all? This question has fascinated physicists for decades, and research continues to this day to determine whether the proton truly has a finite lifespan. If protons eventually break apart, it would have major consequences for the universe, our understanding of physics, and even the fate of all matter. In simple terms, proton decay is a process where a proton, the positively charged particle found in the nucleus of an atom, spontaneously breaks down into smaller particles. This would mean that even the most fundamental components of matter are not truly permanent. According to the standard model of particle physics, which is the best framework we currently have to describe fundamental particles and their interactions, protons should be completely stable. No experiment has ever observed a proton decaying. However, some advanced theories beyond the standard model suggest that protons might not last forever. One such theory is called Grand Unified Theory, GUT. This theory attempts to connect three of the four fundamental forces of nature: electromagnetism, the strong nuclear force, and the weak nuclear force, into a single framework. According to GUT, protons are not truly stable and could eventually decay over incredibly long periods, far longer than the current age of the universe. If protons decay, they would do so through a process where they transform into other, lighter particles. Scientists predict that a decaying proton would break down into a positron, the antimatter version of an electron, and a neutral particle called a pi meson, or pion. The pion then further decays into even lighter particles called photons, or neutrinos, which are nearly massless and can travel vast distances through space without being stopped. This decay process would be extremely slow, so slow that if you had a single proton, you might never see it decay even after waiting for trillions of years. This is why proton decay has never been directly observed. Scientists believe that, if it happens, the half-life of a proton, the time it takes for half of a given group of protons to decay, could be around 1 followed by 34 zeros years, 10 to the power of 34 years. This is much, much longer than the current age of the universe, which is about 1 followed by 10 zeros years, 13.8 billion years. Since the decay of a proton takes such an unimaginably long time, scientists do not expect to see it happen in a normal laboratory setting. Instead, they look at huge numbers of protons at the same time in order to increase their chances of spotting a rare decay event. If proton decay were proven to exist, it would be one of the most groundbreaking discoveries in the history of physics. Here's why it matters. It would change our understanding of physics. The discovery of proton decay would mean that the standard model is incomplete. This would push scientists to develop new theories that go beyond what we currently understand about fundamental particles. It could even bring us closer to a theory of everything, which is a long-sought framework that unifies all forces in the universe. It could explain the ultimate fate of the universe. If protons decay, then all matter, including planets, stars, and even black holes, would eventually break down into smaller particles over incredibly long timescales. This would mean that, in the very distant future, the universe could become a vast, empty space filled only with radiation and fundamental particles that no longer form atoms. It would connect to other unsolved mysteries. Proton decay could help explain why our universe is made mostly of matter instead of antimatter. When the universe began with the Big Bang, matter and antimatter should have been created in equal amounts. However, for reasons that are not yet fully understood, matter became dominant. Some theories suggest that proton decay could be linked to this imbalance. Because proton decay is expected to be an extremely rare event, detecting it requires highly advanced experiments. Scientists build enormous underground detectors filled with massive tanks of pure water or other special materials that can capture the tiny particles produced if a proton decays. These tanks are located deep underground to shield them from cosmic rays and other sources of interference. Super Kamiokande, Japan. A giant underground detector filled with 50,000 tons of ultra-pure water. It is equipped with thousands of sensitive light detectors that can catch the faint flashes of light that might be produced if a proton decays. Hyper Kamiokande, Japan. An even larger version of Super Kamiokande currently under construction, which will provide even better sensitivity. Sudbury Neutrino Observatory, Canada. A detector originally designed to study neutrinos but also used to search for signs of proton decay. Deep Underground Neutrino Experiment, United States. A next-generation experiment designed to study neutrinos and possibly detect proton decay. So far, no experiment has detected proton decay, but the search continues. If it is eventually observed, it would be one of the most significant scientific discoveries of all time. If scientists never find any evidence of proton decay, it would mean that our current understanding of physics is still correct, at least in this regard. It would suggest that protons are truly stable and will never break apart, no matter how much time passes. This would also mean that the universe will never dissolve into pure energy, and matter as we know it will exist forever. However, the absence of proton decay would also challenge many advanced theories, such as grand unified theories. Scientists would have to rethink their models of particle physics and possibly look for other explanations for the mysteries of the universe. For centuries, humans have wondered about life after death. Many religions and spiritual beliefs suggest that our souls do not simply vanish when we die. Instead, they are reborn, either into new bodies or different forms of existence. This idea is known as reincarnation, a concept deeply embedded in various cultures, from Hinduism and Buddhism to ancient Egyptian and Greek philosophies. But what if reincarnation is not just limited to living beings? What if the entire universe itself undergoes a cycle of death and rebirth? This thought-provoking idea is called cosmic reincarnation, a theory suggesting that the universe does not simply end but is reborn in a continuous cycle. Scientists and philosophers have explored this possibility, trying to understand whether the universe has been created once or has existed multiple times in an infinite loop. Could the cosmos itself experience a form of rebirth, much like the idea of human reincarnation? To understand cosmic reincarnation, we must first look at how the universe was born. According to scientists, the universe as we know it began around 13.8 billion years ago with the Big Bang, a massive explosion that created space, time, and everything within it. Over billions of years, stars and galaxies formed, planets came into existence, and life eventually emerged. However, many scientists believe that the universe will not last forever in its current state. The universe is constantly expanding, but will it keep expanding indefinitely, or will it collapse and start over again? This question has led to several theories about how the universe might end and whether it could be reborn. One of the most popular ideas is the Big Crunch theory. This theory suggests that instead of expanding forever, the universe will eventually slow down and begin to shrink. Over time, galaxies, stars, and planets would be pulled closer together until everything collapses into a single, infinitely dense point. If this happens, it could lead to another Big Bang, creating a brand new universe, a cosmic rebirth. Another theory, known as the Big Bounce, takes this idea further. It suggests that the universe has already gone through multiple cycles of expansion and collapse. Instead of a single beginning and end, the universe might be in an endless cycle of rebirth, where each Big Bang is just another chapter in an infinite cosmic story. The idea of the universe experiencing cycles of birth, death, and rebirth is not just a modern scientific theory. It has deep roots in ancient traditions. Many cultures throughout history have described the universe as being part of a repeating cycle. For example, in Hindu cosmology, the universe is believed to go through continuous cycles of creation, preservation, and destruction. According to Hindu texts, one cosmic cycle, known as a kalpa, lasts for 4.32 billion years. At the end of each cycle, the universe dissolves and is later recreated in a never-ending process. Similarly, in Buddhism, time is viewed as cyclical rather than linear. Buddhist teachings suggest that worlds are constantly being formed and destroyed, much like human souls are reborn through reincarnation. Ancient Greek philosophers also speculated about the eternal return of the cosmos. The philosopher Heraclitus believed that the universe was in a state of constant flux, always changing and renewing itself. Later, Stoic philosophers suggested that the universe periodically goes through great cycles of destruction and rebirth. Even in Norse mythology, there is the idea of Ragnarok, a great cosmic battle that leads to the destruction of the world. However, after the destruction, a new world is reborn from the remnants of the old, following the same idea of cosmic reincarnation. While ancient myths and spiritual teachings suggest the universe is reborn in cycles, modern science has explored similar ideas using physics and cosmology. One of the key scientific ideas related to cosmic reincarnation is the cyclic model of the universe, developed by physicists such as Paul Steinhardt and Neil Turok. This model proposes that the universe goes through an endless series of expansions and contractions, much like the Big Bounce theory. Instead of a single Big Bang creating everything, the universe could have existed before, and it might continue this cycle forever. Another intriguing theory is based on quantum mechanics, which suggests that at the smallest levels of reality, particles can appear and disappear in a seemingly endless process. Some scientists believe that if the universe follows quantum principles, it may also undergo an eternal cycle of destruction and rebirth. Furthermore, the second law of thermodynamics, which describes how energy spreads out and disorder, entropy, increases over time, might also hint at cosmic reincarnation. If the universe reaches a state of maximum entropy, where everything is evenly distributed and no useful energy remains, some physicists suggest that a new universe could emerge from the chaos, resetting the cycle. One of the most mysterious questions about cosmic reincarnation is whether a new universe would have any connection to the previous one. When humans are reincarnated, some people claim to remember past lives. Could the universe also retain some kind of memory of its past cycles? Some scientists have explored the possibility that patterns, structures, or physical laws might carry over from one cosmic cycle to the next. For example, if the laws of physics remain the same across different cycles, it might suggest a form of cosmic memory. Additionally, some researchers have suggested that certain cosmic imprints, such as the distribution of galaxies or leftover radiation from past universes, might hold clues about previous cycles. If we could detect these traces, it would provide strong evidence that the universe has been reborn multiple times. If cosmic reincarnation is real, it would change how we view the universe and our place within it. Instead of a one-time event, existence itself might be an endless cycle with no true beginning or end. This idea raises several fascinating questions. Does each universe follow the same path, or do they evolve differently each time? Could there be subtle memories or imprints from past cosmic cycles? The universe has existed before. Could our consciousness have existed in some form before as well? The idea of an endlessly reborn universe might also provide comfort to those who struggle with the concept of death. Just as reincarnation in spiritual beliefs suggests that life continues beyond physical death, cosmic reincarnation suggests that existence itself never truly ends. It simply changes and begins again in a new form. Imagine a future where civilizations scattered across the universe can never reach each other again. A time when distant galaxies, once visible and within theoretical reach, become permanently isolated, drifting apart faster than even the speed of light can bridge. This is not science fiction. It is a real possibility predicted by the laws of physics. This concept, known as the isolation of galaxies, is one of the most profound and unsettling ideas in modern cosmology. It suggests that due to the continuous expansion of the universe, there will come a time when galaxies are moving away from each other at such extreme speeds that even the fastest possible communication or travel will be useless. Civilizations, no matter how advanced, will be forever trapped within their own galaxies, unable to send messages or spacecraft beyond their cosmic borders. Over 13,800 billion years ago, the universe began with the Big Bang, a violent explosion of energy and matter that set everything in motion. In the early years, galaxies formed, stars ignited, and planets took shape. But the most important thing to understand is that the universe itself has never stopped expanding. In the 1920s, the astronomer Edwin Hubble made a groundbreaking discovery. The universe is not static. Instead, galaxies are moving away from each other, and the farther away they are, the faster they seem to be receding. This observation led to the realization that space itself is stretching. For many years, scientists believed that this expansion might slow down due to gravity, perhaps even reversing at some point. However, in the 1990s, astronomers studying distant supernovae discovered something shocking. The expansion of the universe is actually speeding up. This acceleration is driven by a mysterious force known as dark energy, which makes up nearly 70% of the universe's total energy content. Because of dark energy, galaxies are moving apart at ever-increasing speeds. Right now, this effect is noticeable only on the grandest scales. Galaxies within the same gravitational clusters, like our Milky Way and its neighbor Andromeda, are still close enough to remain connected. But in the far future, this will change dramatically. As dark energy continues to push galaxies apart, there will come a time when only the galaxies bound together by gravity will remain visible to each other. Everything else will move so far away and so fast that even light, the fastest thing in the universe, will never be able to reach us from those distant galaxies. Scientists estimate that in about 100 billion years, every galaxy outside of our local group will be completely unreachable. No matter how advanced a civilization becomes, no matter how powerful their telescopes or spacecraft, they will never see or visit those galaxies again. The universe will appear empty beyond their cosmic neighborhood. To make this clearer, imagine standing on a beach, looking out at the ocean. Right now, you can see distant islands. But what if the ocean were to stretch and expand so rapidly that those islands moved away faster than you could ever swim or send a boat? Eventually, they would disappear beyond the horizon forever. This is exactly what will happen to galaxies in the far future, except there will be no way to bring them back into view. This isolation has massive implications for any intelligent life that may exist in the universe. Right now, if alien civilizations exist in distant galaxies, we at least have the possibility of detecting them. Light and radio waves from billions of years ago still reach us, carrying information about what happened in those galaxies long ago. But once those galaxies move beyond our cosmic horizon, even their light will never reach us again. This means that civilizations in the far future will have no evidence that anything exists beyond their own galaxy. If a future astronomer in the Milky Way looks out into space 100 billion years from now, they will see only darkness beyond the local group. They will have no way of knowing that billions of galaxies once existed. To them, the universe will seem much smaller, as if their galaxy is the only one. Even if an advanced civilization wanted to send messages, build spacecraft, or attempt intergalactic travel, they would find it physically impossible. Space itself will be expanding so rapidly that anything sent out will never reach its destination. In effect, galaxies will become self-contained islands, completely separated from the rest of the universe. If we imagine humanity surviving into this distant future, what would life be like? How would civilizations cope with being completely cut off from the rest of the cosmos? Let's take a closer look. A shift in perspective. Future civilizations may grow up believing that their galaxy is the entire universe. Without evidence of other galaxies, they may never even conceive of a time when the universe was much larger and filled with countless galaxies. Ancient records from our time, if preserved, would sound like myths. Resource limitations. With no way to travel to other galaxies, civilizations will be permanently limited to the resources within their own galaxy. They will have to carefully manage their energy sources, planets, and materials, knowing that no outside help or expansion is possible. The search for meaning. Knowing they are alone, civilizations may turn inward, focusing more on their own technological and cultural advancements. Some may see the isolation as a challenge to overcome, while others might accept it as a natural phase of cosmic evolution. The ultimate fate. Over trillions of years, even the stars in the Milky Way will begin to die out. With no new material coming in from other galaxies, star formation will slow and eventually stop. The universe will become colder, darker, and less hospitable. The cosmic event horizon is a crucial concept when discussing the future isolation of galaxies. It represents the maximum distance from which light and other forms of communication can ever reach an observer in the future. Imagine standing on the shore of an endless ocean. If a ship sails far enough away, it will eventually disappear beyond the horizon, never to be seen again. This is exactly what is happening with galaxies in the universe. Right now, we can still see and study many distant galaxies because their light is still traveling toward us. However, as the expansion of the universe accelerates, galaxies that are far enough away will eventually cross the cosmic event horizon. Once this happens, their light will never reach us again, no matter how powerful our telescopes become. From our perspective, these galaxies will gradually fade from view until they disappear completely. In the far future, trillions upon trillions of years from now, the only galaxies that will remain visible to us will be those within our local group, a small cluster of galaxies that includes the Milky Way, the Andromeda Galaxy, and a few dozen smaller galaxies. But beyond this local group, all other galaxies will be lost to the void, unreachable and invisible. This means that if intelligent life exists in another galaxy, billions of light years away, there will come a time when we will never be able to communicate with them again. No message, no signal, no technology will ever bridge the growing gulf between us. The idea of galaxies being forever isolated raises profound questions about the fate of any intelligent life that may exist beyond our own galaxy. Imagine a distant future civilization living in a galaxy far from our own. Right now, they could, in theory, observe the same universe we do. They could look up at the night sky and see countless galaxies stretching across the cosmos. But in the distant future, their night sky will look very different. Over time, one by one, those galaxies will vanish from view until only their own galaxy remains. A civilization living in such a time would have no evidence that other galaxies ever existed. Even if they developed the most advanced telescopes, they would see only darkness beyond their cosmic horizon. They would be trapped in a self-contained universe, unable to know if there was ever anything else out there. This raises a haunting question. Could we already be living in such a universe? Could there have once been countless galaxies that have already disappeared beyond the cosmic event horizon, leaving us unaware of their existence? It is a chilling thought, one that underscores just how fragile our ability to observe and understand the cosmos truly is. As galaxies become more isolated, the universe will continue its journey toward an uncertain fate. Scientists have proposed several possible endings for the universe, each more dramatic than the last. One possibility is known as the Big Freeze. If dark energy continues to accelerate the expansion of the universe, galaxies will keep moving apart until all stars eventually burn out. Without the formation of new stars, the universe will become a cold, dark, and empty place where only black holes and dead stars remain. Another scenario is the Big Rip, in which dark energy becomes so powerful that it eventually tears galaxies, stars, and even atoms apart. In this case, the universe itself would be destroyed in a violent explosion of energy. A third possibility is the Big Crunch, in which the expansion of the universe eventually slows and reverses, causing everything to collapse back into a single point, possibly leading to another Big Bang and the birth of a new universe. No matter which fate awaits the universe, one thing is certain: the isolation of galaxies is an unavoidable reality. As time stretches on, the cosmic landscape will grow lonelier, and the connections between galaxies will be lost forever. For centuries, humanity has pondered the nature of the universe. Is it endless, stretching beyond our ability to comprehend? Or does it have a definite conclusion, a point where everything as we know it ceases to exist? These two ideas, the possibility of an infinite universe and the certainty of an inevitable end, stand in direct contradiction, creating a paradox that has puzzled scientists, philosophers, and theologians alike. The very idea of infinity is overwhelming. It suggests that the universe has no edges, no borders, and no final stopping point. If we were to travel through space indefinitely, we would never encounter a wall marking the end of existence. Instead, we would simply continue on forever. But how does this concept hold up against scientific discoveries, and does it contradict what we know about the fate of the cosmos? To answer these questions, we need to explore both sides of the paradox in depth. The idea of an infinite universe dates back to ancient civilizations. Early Greek philosophers such as Anaximander and Democritus speculated that the universe might be boundless, containing an endless expanse of stars and planets. However, it wasn't until the advancements of modern physics that this idea gained serious scientific consideration. Today, many scientists believe that the universe might be infinite in size. This belief comes from the concept of cosmic inflation, a theory that suggests the universe expanded at an unimaginable speed in the first few moments after the Big Bang. If this expansion was truly limitless, then it means the universe could stretch on forever. One key argument in favor of an infinite universe is the observation of cosmic uniformity. When astronomers look in different directions through powerful telescopes, they see galaxies spread out in a pattern that appears endless. There are no signs of an edge or a boundary. The cosmic microwave background radiation, the faint glow left behind from the early universe, also appears to extend indefinitely, adding more evidence to the idea that the cosmos has no limits. Additionally, the theory of parallel universes, or the multiverse, suggests that our universe might be just one of many within an infinite sea of realities. If true, this would further reinforce the idea that existence is boundless, containing an infinite number of variations of space, time, and even versions of ourselves. Despite the compelling arguments for an infinite universe, modern physics also provides strong evidence that the cosmos, as we know it, will eventually come to an end. The contradiction between these two ideas is what makes this paradox so intriguing. Scientists have proposed several theories about how the universe might meet its ultimate fate. One of the most widely accepted ideas is the heat death theory. This concept, rooted in the second law of thermodynamics, states that over an immense period of time, all energy in the universe will spread out evenly. As a result, there will be no temperature differences to allow useful work or movement, and everything will reach a state of complete stillness. In other words, the universe will become a dark, cold void where nothing happens, a frozen, lifeless expanse stretching into eternity. Another possibility is the Big Crunch, which suggests that the universe's expansion will eventually slow down and reverse. If this happens, everything, galaxies, stars, and planets, will begin collapsing back into a single point, much like the conditions before the Big Bang. This would mean that the universe is not infinite, but rather cyclical, expanding and collapsing over and over in an endless loop. There is also the terrifying idea of the Big Rip, a scenario in which the universe's expansion speeds up so much that it eventually tears itself apart. If this theory is correct, there will come a moment when galaxies, solar systems, planets, and even atoms will be ripped apart by the overwhelming force of expansion. In this case, the universe would not just stop functioning, it would be completely destroyed. Lastly, some scientists consider the possibility of quantum decay, in which the universe could experience a sudden and unpredictable collapse due to changes in the fundamental nature of space itself. If a more stable form of reality exists, our universe could be swallowed by it in an instant, erasing everything we know without warning. At first glance, the idea of an infinite universe seems impossible to reconcile with the certainty of an eventual end. However, many physicists argue that these two ideas might not actually be in conflict. One way to resolve this paradox is to recognize that infinity does not necessarily mean permanence. The universe might be infinite in space, but still have a definite timeline in which it evolves, changes, and eventually reaches an end state. Just because something extends forever does not mean it must always remain the same. Another perspective comes from quantum mechanics, which suggests that space and time may not be as rigid as we once thought. The fabric of reality could be in constant fluctuation, meaning that while the observable universe might eventually fade, new universes could be born elsewhere. This ties into the theory of the multiverse, where the destruction of one universe might simply lead to the birth of another, continuing an infinite cycle of existence. Additionally, if time itself is an emergent property rather than a fundamental aspect of reality, then the concept of an end may not be as absolute as it seems. Some scientists speculate that time may not function in a linear way at the deepest levels of reality, which could mean that an end is merely a transition to another form of existence beyond our understanding. Beyond the scientific theories and complex equations, this paradox has deep philosophical and emotional implications. As humans, we struggle to grasp the concept of infinity because our everyday experiences are finite. We are born, we live, and we die. Everything we know has a beginning and an end. The idea that the universe might continue endlessly is difficult to imagine, yet so is the notion that everything will one day cease to exist entirely. This paradox also raises profound questions about our place in the cosmos. If the universe is infinite, does that mean we are insignificant? Or does it mean that life is even more remarkable, a rare and precious phenomenon within an endless sea of existence? And if the universe will one day end, what does that mean for everything we have built, discovered, and cherished? Religious and spiritual beliefs also play a role in how people interpret this paradox. Many religious traditions describe the universe as having a divine beginning and an ultimate purpose, while others suggest that existence is part of an eternal cycle beyond human comprehension. Whether through faith, philosophy, or science, humanity has long sought answers to this ultimate question. Throughout history, humans have sought to understand the mysteries of the universe. From ancient civilizations studying the stars to modern scientists unraveling the fabric of space and time, our curiosity has never wavered. But as we push the boundaries of knowledge, we find ourselves facing ideas that challenge everything we once thought was possible. Exotic physics is one such frontier, a field that explores phenomena that defy conventional understanding. And as we approach what some call the endgame of scientific discovery, exotic physics may hold the key to unlocking secrets that could shape the fate of humanity and the universe itself. Exotic physics refers to theories and discoveries that go beyond the laws of physics as we currently understand them. While classical physics, established by scientists like Isaac Newton and Albert Einstein, explains most of what we observe in daily life, exotic physics deals with concepts that seem almost supernatural. These include ideas like negative energy, extra dimensions, wormholes, and even the possibility of parallel universes. Some aspects of exotic physics remain purely theoretical, meaning they exist only in mathematical equations and have yet to be proven through experiments. Others, however, are beginning to show signs of being real thanks to advances in quantum mechanics, particle physics, and astrophysics. The more we uncover, the clearer it becomes that reality is far stranger than fiction. When scientists talk about the endgame in physics, they are referring to the final stages of our quest to fully understand the universe. It is the idea that we are approaching a moment in history when all the fundamental laws of nature will be revealed, allowing us to manipulate reality in ways once thought impossible. The endgame is not necessarily about destruction or collapse. Rather, it is about reaching a point where humanity either masters the forces of nature or faces challenges too great to overcome. Some believe that exotic physics will be the deciding factor in this final stage. If we unlock its secrets, we may be able to achieve technological advancements that could allow us to travel through time, explore other dimensions, or even harness infinite energy. If we fail, we may hit an intellectual wall, unable to move beyond our current limitations. One of the most fascinating ideas in exotic physics is negative energy. Unlike regular energy, which powers everything from light bulbs to rocket ships, negative energy has the strange ability to bend space and time in ways that defy logic. Physicists have proposed that negative energy could be used to create a warp drive, a technology that would allow faster-than-light travel. If such a system were possible, it could enable humanity to explore the farthest reaches of the universe without taking thousands or even millions of years. The concept was first introduced in the early 1990s by physicist Miguel Alcubierre, who suggested that a bubble of warped space could push a spaceship forward at speeds faster than light without violating Einstein's theory of relativity. If exotic physics can make warp drives a reality, the endgame could bring about an era of interstellar exploration, where humans colonize distant planets and make contact with extraterrestrial civilizations. However, if negative energy remains beyond our grasp, we may be forever confined to our small corner of the cosmos. A wormhole is another bizarre concept in exotic physics. It is essentially a shortcut through space and time. a tunnel that connects two distant points in the universe almost instantly. Einstein and physicist Nathan Rosen first theorized about wormholes in the early 20th century, but so far, no one has discovered a naturally occurring one. However, some researchers believe that if we could create or stabilize a wormhole using exotic matter, we could revolutionize space travel. Instead of taking centuries to reach another star system, a spaceship could pass through a wormhole and arrive in mere seconds. The role of wormholes in the endgame is clear. If we figure out how to harness them, distance will no longer be a barrier. But if they remain a theoretical dream, space travel beyond our solar system may remain impossible. One of the most mind-boggling ideas in exotic physics is the possibility of a multiverse. Instead of one single universe, there could be an infinite number of parallel realities existing alongside our own. Some scientists argue that every decision we make creates a new branch in reality, meaning that an infinite number of versions of ourselves might exist in different universes. Others believe that entirely separate universes with different physical laws may exist beyond our own. If the multiverse is real, it could change everything about our understanding of life and existence. Some theories even suggest that advanced civilizations in other universes might have already discovered ways to travel between realities. The question then becomes, can we do the same? If so, the endgame could involve humanity expanding beyond a single universe and exploring realms we never imagined possible. Another possibility in exotic physics is time travel. Many scientists dismiss it as impossible, but some theories suggest that time travel might be achievable under certain conditions. One of the biggest problems with time travel is the paradoxes it creates. The most famous is the grandfather paradox. If you travel back in time and prevent your grandfather from meeting your grandmother, you would never be born. But if you were never born, then you could not have traveled back in time to change history. Some physicists believe that parallel timelines or self-correcting timelines could solve these paradoxes, making time travel theoretically possible. If we master time travel in the endgame, it could lead to unimaginable possibilities, from preventing catastrophic events to witnessing historical moments firsthand. While exotic physics offers incredible opportunities, it also comes with serious risks. If we gain control over these forces without fully understanding them, the consequences could be disastrous. One of the most terrifying ideas in exotic physics is the possibility of a false vacuum collapse. According to some theories, our universe exists in a stable energy state, but if it were to suddenly shift to a lower energy state, everything could be destroyed in an instant. If scientists unknowingly trigger such a collapse while experimenting with exotic physics, it could mean the end of not just Earth, but the entire universe as we know it. If exotic physics allows us to travel across the galaxy or communicate across dimensions, we may eventually make contact with intelligent extraterrestrial beings. But not all civilizations may be friendly. Some experts warn that advanced alien species could see us as insignificant or even as a threat. If we blindly reach out to other civilizations without caution, we could invite dangers we are not prepared for. Messing with the fundamental fabric of reality could have unintended consequences. If we create wormholes or travel through time, we may accidentally disrupt the natural order of the universe, leading to unknown and possibly catastrophic effects.